Hi, everyone. Thanks for coming and thank you for watching this online. This is the second day of the Data-Centric AI Workshop, jointly hosted by Stanford HAI and the ETH AI Center. So before I start, right, we just want to emphasize how grateful we are to all the student organizers. This event won't be possible without their work and all their leadership. I think I speak for all the professors involved that every day we feel privileged to work with great people like all of them in these two great universities. So also, we are also grateful to all of our keynote speakers, right? So you hear some of them talking yesterday, and we are going to have even more today. Okay, so and for those watching online, right? So there is the Slido thing on the HI website. If you have any questions, any comments, just input them. We are going to ask your questions to our keynote speakers after their talk. Today, we are going to also have a very small but very interesting local event. We are in this very cozy industry feeling room, right? And we actually have some local audience. Right? We will also get questions from the local audience. Yeah, so let me just quickly recap, right? So why we are doing this workshop, right? So essentially over the last couple years, right? So I think everyone here really feel the shift of building machine learning applications, right? So once upon a time, you have a data set, you train a model. If you are not happy with the quality of this model, what should you do, right? You twist your model, right? So recently we see the shift from this more model-centric view to a more data-centric view, right? So usually there are actually two different cycles. When you're developing your models, right, when you are not happy with the quality of your model, instead of twisting the model, you start to twisting the data. You do data cleaning, you do more data acquisition, you do weak supervision, right? And once you deploy your model, right, because you have this data cycle going on, inevitably you have a stream of model pushing into your system, and you have a stream of production data coming into your system. And together, you also have another loop being continuous, essentially like adaptation and also testing. So given this, right, so you see there are a lot of new challenges, a lot of new problems, but there are also a lot of new opportunities. And that is why together with our colleague at Stanford University, we organize this workshop, really try to bring the experts together to talk about how should we deal with all those challenges and take advantage of all those opportunities. So yesterday was the first day of the workshop. Today, we have another exciting 7 hours of content, right? We will start from European afternoon, and we will go all the way until Pacific noon, right? Which is very exciting. So there will be 5 hours hosted at ETH. So in the first session, we are going to talk about some problem related to data quality and data systems, and what is the implication of supporting machine learning. Like in this session, we have two great keynote speakers, and Cedric and Bojan also talk a little bit about the thing that on our side, and we have student research highlight talks, right? So another session after this is about AI regulation and governance, right? So there's all those regulations coming in, and how can we accommodate like all of those, and how can we build machine learning systems that are really trustworthy. So we have two great keynote speakers with student highlight talks, and then we have a panel about AI governance. We have a great collection of panelists to really tell us what they think about AI governance. And in the middle, we have 4 startups joining us locally and try to give us their pitch about how they think about data-centric AI, and we are going to have a quick break in the middle. And then after this, we have 2 hours hosted by Stanford. In the first session there, we are going to talk more about the benchmark effort that we have all together. We are going to talk more about detail of DC bench together with some research highlight talks, and then we have another 2 great keynote speakers after that. So this is today, very exciting 7 hours of content. So now let's start our first session, right? So now let me transition to Felix, where I introduce him. Hello. Okay, great. Felix, do you want to share your screen?
Sure. 1 second.
Yeah, so it's our great honor to have Professor Felix Naumann join us today. Felix really doesn't need any introduction, right? He's a professor in Hassel-Plattner Institute, and he's really a world expert in many problems related to data quality. For example, data profiling, data cleansing, data integration, right? When I was undergraduate student 10 years ago, I read his papers, and today I still do, right? So really looking forward to hear what he has to say to all of us. Yeah, Felix, the floor is yours.
Thank you very much, and thank you for the invitation. I'm assuming right now you can hear me well, and you can also see my first slide. Yeah, I can see the monitor. So thank you very much, and I'm very humbled, and it's great to hear that you still read my papers. That's of course very nice, and the same goes back, of course. So I want to give a quick overview. You don't have much time. I gave the title Bad Files, Bad Data, Bad Results. This is in a sense guided by the current research that we're doing in this area of data quality and data cleaning. But I think the most interesting parts are my outlook. So I won't be presenting many solutions, but I think I hope I will give you an additional perspective on data quality and information quality, since that is something that I've been working on since my PhD, literally. So I don't know, 20 years ago or whenever that was. Okay. So don't worry, this is the only slide I'm going to show to mention, yes, we have big data and we want to do machine learning. I just want to point out that basically this fourth paradigm, this data intensive or data oriented paradigm, is the one that enables us to do machine learning and AI. And in a sense, it's the one that supposedly will never happen, will relieve us from any theoretical science, because we can just trust the models to know and to predict, and we don't really need models anymore, right? I don't share that particular vision, but in a sense, that's where we're going. I do want to show this data science pipeline. This is kind of a typical pipeline from capturing data, extracting, cleaning data, and then all the way to querying or analyzing the data. And I boldly put down my distinction of data engineering and data science. And today we will be talking about two areas. One is, in essence, this area at the bottom left, and then a little bit about this area on the top right, right? But of course, all of these individual blocks here deserve research attention of their own. I'm sure many of you have seen this slide, so again, I'll just be very quick. It's a well-known problem, and you can see this is from 2016, but this survey is repeated over time, and the numbers seem to keep growing, that researchers and data scientists spend most of their time in collecting data and cleaning data, right? And this is often collectively referred to as data preparation. And then, as you all know, this is also the least enjoyable part of their work. And I can agree. So I fall exactly in this distribution of, let's say, data scientists. Even if I don't want to call myself a data scientist, I spend a lot of time, fiddling with the data, but also, which is often not really considered very well, is this collecting data sets, which sounds like you just go out and download some stuff. But as I'll show you, it's not quite that easy. It's not just about cleaning, it's about actually getting the data is also quite difficult. So data preparation has been known for a while, and this is a screen of lots of tools, and we did a big survey on data preparation tools and their features. So I only want to show this slide to show you, there's many things that need to be done to do data preparation. All of these are kind of capabilities of these different systems, right? And you can see here on there's some of the maybe more important representatives, but there are also many more. So this is a collection of tools that we have gathered, all in a sense dedicated to data preparation and data cleaning. And these are just the industry tools. So I'm ignoring completely here the research advances that we have seen in the past. Okay, so data preparation is an important topic. So I will be talking about bad files. It's kind of a pet project of mine that I like to talk about, because it's kind of, I think, underrepresented in research, but overrepresented in my daily work and maybe also your daily work. It's the problem of different data formats and, let's say, buggy CSV files. So this is a slide just to show you, if you download data from data.gov, these are all the different formats that you might observe your data in. And awfully, the most common one is HTML. I mean, that's nothing that I want to deal with, or even worse, a PDF or TIFF files. So this is all not really data. These are images of data, but not really data. And CSV, I don't even know where CSV, oh, CSV is right here, but you also have text files. So it's just a huge amount of types of data that you need to deal with. But if we only concentrate on, the supposedly nice files like CSV files, this is a table that you could download from a data government source. So you think, oh, this is kind of cool. This is about departures of nationals. So, how many people are ejected from what country to which country, refugees, etc. So it sounds very important and interesting, and you get a lot of numbers. But then if you have a look, you will find out that there's some, larger numbers, and those are in fact totals, right? These are totals globally, and then total Africa, total per continent, etc. Right smack in the middle of that data. And then if you scroll down, this happens again and again, that you have aggregates hiding in your data, right? And you need to figure this out. You need to recognize, okay, these lines are actually should be deleted if you want to do anything reasonable with the data. It's another fun example, right? This is stuff you don't realize until you try to load and work with your data. This is, again, a real world example where somebody just hid some values by typing in a string. Catastrophe, of course, for data scientists, because they have to, fiddle around a lot to, let's say, replace the string with something else, right? Then you have situations where you have spreadsheets with lots of tables. So here's a spreadsheet. You might all recognize, okay, this is kind of stuff you might be looking at. And there's lots and lots of different, let's say, tables or parts or pieces of data hidden in this spreadsheet, right? And we are, in fact, doing research to try to recognize these kind of things, right? So these are some more examples. So you can see, CSV files, they're all over the place. They contain metadata, they contain footnotes, they can contain aggregations, et cetera, et cetera. So if you want to handle this data, you will need to recognize, okay, where is actually this data, and how can I extract it from these files, right? So we've been working on this for a while now. This is even worse. So if you look at the middle file here, I mean, this is something I'm sure all of you have seen, right? So this is nice for a human to kind of read the table. You have these nice separators and pipe symbols, right? But of course, for a system, this is a catastrophe, right? And then here on the top left, you can see another format where things are kind of tab separated, right? But the different number of tabs between columns. Again, you want to recognize this. And then here comes the kicker. Both of these tables come from the exact same file that we download, right? So you have many different kinds of things per file. Okay, so this is a bad situation. There's all sorts of stuff you can do. I'll just briefly highlight two. So one thing is that we want to automatically recognize tables. So we do this kind of image-based. We represent each non-null value as a pixel, and then we kind of cluster the pixels to see, okay, these are the tables, right? And then we go a step further and we do this per file, and then we recognize templates. So you can see actually that many of the files stem from the same template, so you can extract them in one go, right? So if you know how to parse one of those files and the others follow the same template, you can extract data from those as well, instead of being frustrated again and again by each new file, right? Another thing that we're trying to do now is we're trying to actually benchmark the ability of systems to load data in various formats and shapes and with various errors, right? So this is a screenshot from Pandas where you're trying to load some data and then you get a parse error for whatever reason, right? And what we do is we generate a lot of data with specific problems and then just run these import scripts for any kind of system again and again and again to find out, what kind of problems can a system handle and which kind of problems can a system not handle, right? And we're looking at databases, visualization tools, programming frameworks, et cetera, et cetera. And we're trying to benchmark and see how flexible are these systems, or how, let's say, kind are these systems to data scientists. In one sense, this is a way to measure, but it's also, of course, a means to improve these systems. So we can point out into specific errors, and then we're trying to, let's say, push research and push systems developers to be able to handle, let's say, more diverse data through specialized methods, right? Here's a little bit of a glimpse into these benchmarks, and we actually did a huge study. I think we looked at 3,000 files, raw data in the wild, and we can see that many of them do not follow a typical CSV standard, but are all over the place use different kinds of encodings, have more than one table, have table headers that are more than one row, all this stuff we can observe. Okay. Last problem I wanted to point out before we turn to the typical data errors, right, is this problem of data aggregation, as I mentioned. So again, you want to recognize these kind of aggregations. They can happen all over the place in your data. It looks like data, but in fact, lots of this is redundant. And what is even worse is that many of the aggregations we see and we manually check actually have errors, right? So these are typically like rounding errors, but they can get quite large and propagate. So we see errors in raw data with wrong aggregations up to 37% error rate in their aggregation. So again, this is kind of scary and goes a little bit already into this problem of not difficult formatting, bad files, but actually bad data, right? So I want to kind of transition now from what I would call data prep, which is more syntactic transformation, getting the data ready to load, getting the formats right, to actual data cleaning that is correcting errors in the data. So the data might be formatted perfectly fine, but it's just wrong, right? There might be actual errors in the data, and which is more of a semantic problem, and where I think data cleaning is then the more appropriate term. So let's move on to bad data. Again, I'll motivate a little bit of what's out there. Data cleaning is has a long-standing tradition, of course, in database systems. And I'm not going to survey, even a tiny bit of this, but just show you some kind of fun examples. And then I'll show, or I'll try to show, why it's important to deal with these, right? So this is a fun example I always like to show. So first, in the background, you see lots of different ways that the word Britney Spears is spelled. I'm just imagining, these teenage girls typing in Britney Spears and not knowing how to write her name. And this, of course, leads to bad data. If you enter this kind of data into a spreadsheet, let's say, or into a database, you won't be able to identify people, right? And the bottom right example is always kind of cool. So this is, a guy called Debojyoti who apparently breaks lots of laws and speeds all over the place, not just in Ireland, but worldwide, until maybe the Polish people among you recognize that the word Debojyoti actually means driver's license in Polish, and it's not the name of the guy speeding here, right? So again, a typical data error. These are some more data errors, and this already leads to poor learning capabilities. This is where you could register for an event, and you have to give your country, and somebody just downloaded a list of countries from the web, apparently, including lots of countries that were not existing anymore. Like, for instance, in my case, the German Democratic Republic, right, was long gone in 2010, but you could still say that's my home country. Or you have all these versions of Ireland. You still had Yugoslavia as a country, and many, many errors, right? So the problem here is, of course, you can imagine how much fun people had in entering a strange country. And then you can also imagine how much fun the data analysts had to figure out how many people from which country are visiting or attending this FIFA event, right? So again, a nice source of quality errors. These are all kind of fun. This is a real-world data set or an analysis of a real-world data set where you really get into wrong analytics, right? So what happens is, if you have a database for persons, right? So this is a typical schema. You have name 1, name 2, name 3, I'm not the schema designer here. And then you have city and district and street, etc. All this stuff, right? And in the rows here, we have, or my colleagues here have put the type of information that they found in those respective fields, right? So for instance, they found mobile phone numbers many times in the district field. Why? Because there's no mobile phone number column in this data set, but the district, who cares about the district as long as you know, let's say, the city and the zip code? You don't care about the district. So district is kind of a free floating field. So you might as well enter the phone number into there, right? And you have all sorts of stuff like the embargo flag, basically saying, there's a string, do not deliver, right? And they put that string all over the place, right? In the first name, second name, and things like that. So then if you have a database like this, try doing any kind of customer analysis, right? You need serious cleaning to clean up all this, in a sense, junk that you can find, right? Loading points, credit information hidden in the name field, etc., etc. So this already goes really towards the data analytics and shows you how important it is. And the most general definition of data quality is fitness for use, right? So clearly this data is not fit for use, but we want to dig a little bit deeper and find out, okay, what does fitness for use actually mean? So this is kind of, this fitness for use is kind of the starting point for the whole information quality community, which is usually situated not so much in computer science, but in information systems, or in German Wirtschaftsinformatik, right? And there's a strong research area in this, and many people have done a lot of good research. And I think it starts to become more and more applicable because we're moving away from databases where we just think about data errors towards larger systems where more dimensions are relevant. So the traditional thing that we guys from database think about is incorrect data, and then you measure that as in terms of accuracy, let's say. Or we have missing data and you measure it in terms of completeness. This we understand. And then my addition from earlier on, poor formatting, there's this notion of representational consistency. Okay, this is something we can measure. But then, these researchers, they go on, they say, okay, there's other dimensions like the timeliness of data, right? Which is nothing that you can actually observe in the data. It's some metadata that you know. Or the data comes from an unknown source. Or it's hard to reach. Or there's a slow connection. All these are, in a sense, dimensions that tell me something about the information quality, not so much about the correctness of the data, but how easy is it to use, how likely is it that I will use it, and how bad are my trained models going to be if I use them. Let me go back. Yeah. So there's a seminal paper by Richard Wang and Diane Strong about data quality dimensions from a more, let's say, holistic point of view. I'm not going to read them all out, but you can clearly see that most of them are not what we computer scientists are let's say, comfortable measuring and dealing with, like, as I said, reputation or understandability of the data. These are things that are difficult to measure. And I would argue there's more, right? Things like, is there a documentation, right? What is the response time? What is the cost of the data? Why is this all relevant? In my point of view, because data scientists might typically choose the path of least resistance. So what is the trade-off of choosing a data set that is easy to download, but has a lower information quality or lower accuracy, let's say? What is the trade-off of not understanding your data in the documentation versus then using the data to train a model? So I think all these typical information quality criteria suddenly become interesting. So I'm running out of time a little bit. So let me go to the next few slides about bad results, and then I'll be closing in just a minute, right? So we have not only those dimensions I mentioned, arguably there are lots of new AI-specific data quality dimensions that we need to look at. Things like, as we know, bias or diversity, privacy, ownership, who owns the model, who owns the data, who is liable for model mistakes. These are all dimensions that spread the notion of information quality, but work in a very similar way in our systems, right? So below we have a data pipeline. It's more or less exactly what Jay just showed earlier in the introduction slide. So you have training, you build your model, you maybe have some validation data to tune your model, and then you have application data and you deploy your model, right? And these different dimensions that I have earlier, they apply to different situations, right? So liability might be liability for the application, but also might be liability for the quality of the training data, right? A bias can happen, of course, on both the acquisition phase, but also during deployment. Yeah? Diversity plays an important role during the training process, et cetera, et cetera. So what I'm trying to say is there's a huge number of quality dimensions that we need to look at, and we need to suddenly not only apply them to this one pot of data that we have in mind, we need to apply them to the whole, let's say, data science pipeline or machine learning pipeline. Last slide, open research questions, right? Which established quality dimensions are relevant? Which new dimensions do we need to look at? And where do we look for them across data sets, not just within one data set, right? Next is we need to be able to assess them. How do you assess reputation of a data source, right? difficult, right? And we need to explain data quality. We need to explain why we think this result is not quite as valuable as another result in terms of all these dimensions, right? We want to measure efficiently. We need to maybe correlate model errors with data quality problems, right? So the model does not produce good results. Why is that the case? And exactly as Jay just said, might be poor data quality, might be poor model quality, but it might be something in between as well, right? So right now, what are we doing? We're trying to empirically look at this. So we're looking at different tasks like classification, clustering, different methods, traditional data mining, pattern mining, to decision trees, deep neural networks, etc., and all the quality dimensions that I just mentioned. And we're trying to empirically chart the correlation or the influence of among all of these, right? And this is a kind of an ongoing project, and I don't have any results to show yet, but I think there's plenty of research opportunities in this domain. And with this, thank you for listening and attending. I'm looking forward to your questions.
Thanks a lot, Felix. It's a great talk. So let's take some questions, right? So we have a local audience, we have an online audience. But before we go to those questions, I will take the privilege to ask you the first one, right? Sure. So I will talk about data quality. And that's actually something that I think our database community are working on in the last half a century, right? So it's really hard, right? Mm-hmm. And now we start to put that together with a machine learning components after that, right? Mm-hmm. So, and then we start to jointly analyze these two components. So what do you think? Is machine learning make the life of data quality researcher easier or harder? Or it's just on a different dimension that not really comparable? Right?
Yeah. So first of all, in some sense, of course, you could say it makes life easier because there are, in turn, of course, lots of, let's say, ML-based data cleaning methods. So we're discovering new ways to clean data, which is great, right? That's fine. I mean, HoloClean being one of the great examples, but there are other systems out there as well. So that's one thing. So number one is it's becoming more important than ever. Why? Because data quality suddenly has an indirect influence that is hard to fathom, right? So before we could see, okay, here's a wrong address and the letter is returned. Okay, you can see that, we can try to correct it. But suddenly data quality has a more indirect influence on the trained models. And of course, simply because models tend to start to dominate our lives more and more in our everyday digital lives, let's say, which is why this research has become more important. But it has become more difficult, I would also agree, because suddenly more dimensions than the traditional ones become important. And we need to measure at more different places. We can't just say, oh, here's my Oracle database, let's measure data quality. That's just not enough anymore. That doesn't cut it anymore. So yes, it's become more difficult, but that's why we're doing research, right? To tackle the difficult problems.
Great. So we have a couple questions, actually. Let me take one online, right? So could some of the difficulties in fixing bad data lie in the lack of knowledge by the broader community of query languages that can deal natively with heterogeneous dataset or on a higher level than Python and Pandas? So I'm thinking about JSONic, qquery, etc.
Mm-hmm. Yeah, I mean, these are all those point to solutions. So I'm not saying that the state of research and the state of tooling is a catastrophe and we need to start from scratch. That's not what I'm saying. So yes, there is, we're not the only ones doing data preparation research, though there is a lot of research going on. To be honest, I'm not aware of JSONic, but I'm and the tools that you mentioned, but sure, if these are methods that you can apply early on, I'm all for it. But I'm also quite skeptical because the devil is always in the detail, right? I'm guilty of this myself. So we publish new methods, develop new systems that really work well in this particular use case, but either these methods don't make it into production, right? They're just not picked up by big companies that actually handle tons of data, or they just work only for the use cases that we had in mind. And it's kind of the nature of data and information quality that everything is surprising, right? You have in mind a few problems that you want to fix, but as soon as you fix them, along comes a new set of problems that you never even thought of. So I think we're also never going to be done with this, to be honest.
Cool, great, great. So is there any questions from the local audience? We have time to take one. Oh, yeah.
So in this research direction, what would be like a holy grail of, holy grail research result in the direction of data cleaning or this kind of thing?
Yeah. Holy Grail, I don't know. I think it's a very good question. For sure, the Holy Grail is not, in my view anyway, being able to fix all data quality problems, let's say in the training data, to have a method that will guarantee you this data is perfect. I don't think that's the Holy Grail because you're probably doing too much. I think the Holy Grail is to find a trade-off between model quality being good enough and what do I need to fix at which stage in the pipeline leading up to it. I think that's maybe not the Holy Grail, but it is, if we understand how to clean and where to clean to reach our goal, that will be good. That would help, I think, a lot, save a lot of work. I think we're cleaning many things that are just unnecessary to clean also, right? And so being able to trade these things off would be great.
Thank you so much for joining us, Felix. Yeah, thank you.
Okay, it was my pleasure. So thank you. Looking forward to the next set of talks.
Yeah, thank you. Okay, great. So now let's transition to the next speaker.
Hello.
Okay, great. Yeah. So Felix talked about essentially data quality, right? So in our group, we have been working on this for a while, really try to understand like how to combine these two. It's very, very hard. So I think for the next talk, we have two students from our side, Bojan and Cedric, who are also the co-organizer of this great event, right? So, and tell us a little bit what we know about the intersection of data quality and machine learning and the relationship to the larger community vision of data-centric AI. Yeah.
Yeah, thank you very much. So as we said, I'm Cedric and this is Bojan. You will see him for the second part of this talk. So thank you very much for this very interesting talk, Felix. You're going to see many aspects you mentioned in our talk again. So I'm curious to see whether you also have something to say afterwards. So we as a group, we've been working on data quality, mainly in the area of ML development and ML operations. So to get back to the picture Ce had at the beginning, we see two cycles usually in order to make tools for users to support machine learning workflows more efficiently. So on the one hand, we have the development cycle, where users typically have some training data, they train a model, they evaluate their model, and if they're not happy, well, they iterate on the data, and they start over again, right? On the other hand, on the production side or operational side, you have a bunch of models and a production data stream. You then use this stream to test or adapt models in order to pick the model you should choose at the right moment. And then you do this over and over again. So over the years in our group, we've been unfolding those two cycles by investigating many small projects. On the development side, we've been conducting projects which basically treat parsing and augmentation, how to do this efficiently, which tackle the problem of how to perform a feasibility study or to do labor efficient data cleaning or data debugging. Once you're happy with your data, you run through an expensive AutoML system to get your model for production. On the operational side, we have a project which deals with continuous integration and more specifically in how to provide statistical guarantees for your model to pass some requirements. And then once you have a set of candidate models, you want to be able to choose which model to use at a given day. So what we realized is that all those projects have a common theme. They care about how to improve or use data accordingly, which are data quality or management aspects. I'm not going to be able to go into all details, but if you want to know more about the big picture, go to this URL. In our talk, we're going to focus on two data quality aspects, which we have been working on in the data cycle. So going back to Felix's talk, we know that in traditional data quality, there are multiple dimensions. So we have data, which might be noisy or inaccurate, which might not be complete, have some null values. which might not be right for the current task, so outdated, not timely. And finally, they might not meet some consistency rules. But what we care in machine learning is we take that data, we train a machine learning algorithm, and we get a machine learning model, which we measure with some metric of which we care about. So the question is like, how does those quality dimensions propagate to the machine learning training? And what we saw, and this is in line with what has been discussed before, is that defining data quality for machine learning is easier and harder. So we believe it's easier because we have a metric we care about. We know exactly, we can measure it after having trained the model. But we also believe it's harder because of the things Felix said, but also because you need to combine the knowledge of two research directions, of two communities. Data management, which knows a lot about data quality, and which knows that there are more dimensions we need to care about, and machine learning, which is in itself statistically, there are many aspects which you need to take into account. So the two questions we care about in this talk are related to data quality and machine learning, are whether my data is good enough to meet some requirements, and if not, what should I fix? Where should I spend my time? So the outline of this talk is going to follow a very clear pattern, and that is that first we're going to show to you like why do our users even care about those questions specifically? What functionality we do enable by answering those questions, and finally why it is challenging to answer those questions and to provide tools and guidance. So once again, inspecting data quality needs a combination of theoretical and systems research, and you will see this over and over in our talk. Let's start with the first question. The first question we want to answer is what is the best accuracy that any machine learning model can achieve on my data? To answer this, we've been working on a project which we call ISML Snoopy, which performs a feasibility study for ML. And this has been joint work with many people, but most notably Luka Rimanic, which is a postdoc in our group. So a few years back, we had a user with a real struggle. The scientist had some data and tried to do machine learning with that data. After days of trying out ML tools, he wasn't happy with the accuracy he got, so he asked us for help. Sure, because it's our user and we're friendly people, we helped them and we started looking at the data ourselves. And after some days, we started asking ourselves whether the labels are really correct, because we saw that similar features have very different labels. Now, asking the scientists back, they realized, yeah, okay, they're not that correct. So the question is, how can we prevent this from happening? And by this, I mean scientists running out ML tools whereas their data is not good for machine learning at all, or asking us for help. So the functionality we want to enable, if you have a user with some data, which might be noisy or not complete, the user has the goal to use machine learning to get a high accuracy model. But now the data has some limitations, which might be bigger than the expectations you can get from the machine learning model. So we want to answer whether this is actually true as quickly as possible in order for the user to prevent to run costly AutoML system or spend a lot of time, but start fixing his data. So what do we know? So from a machine learning perspective, the quantity we care about is the base error rate, which is the irreducible error. That being said, we have one additional assumption, which is that the training and testing come from the same distribution. That is an assumption of the base error rate. But just a short recap on the base error rate. So if you have a two-dimensional discrete space, then every cell here gets typically assigned to one or another class. And if we have two classes here, the orange and the blue one, then any machine learning model will make at least the blue amount of errors for that cell. If you take the integral over this space, you get the base error rate. So why are there even multiple possible classes in a single cell? Well, there are many reasons. So either you have missing features or you have noise in the features or labels. There has been decades of coming up with practical estimators for the base error rates. So is it solved then? Well, not really, because when we started looking at those base error estimators, there's a clear gap between theory and practice. So first of all, the base error estimators are typically only evaluated on small synthetic data sets. When we go to large real world data set, the question came up like, how do we choose the hyperparameter for those estimators? And how computationally efficient are they? Secondly, base error estimators are known to be very sensitive to the representation you use, but which one should you use then? And finally, the estimators usually give you some bounds which are known to not be tight in all cases. So how can you still use that as a signal to perform a feasibility study? To bring this together, we need to understand the theory and bring it into a practical system. And we did that by having 3 distinct research projects, which we did over two years. The first one was what system we called Phoebe, or framework we called Phoebe, which is for evaluating base error estimators on real world data. So we wanted to understand how sensitive are the base error estimators on real world data with respect to hyperparameters, and how computationally efficient are they. So the key insight we got is that simple estimators with on top of today's pre-trained transformations are very powerful. So we're lucky because today we have access to a lot of pre-trained transformation using sources like TensorFlow Hub, PyTorch, or even Hugging Face. Another thing we realized that those simple estimators are very insensitive to hyperparameters and computationally efficient. If you want to know more, please have a look at our paper, which is published at this year's NeurIPS. So now we saw that these simple estimators work on top of pre-trained embeddings, but why are we even allowed to use other transformations than the raw data? To understand this question, we did some theoretical analysis, and the key insight we have here is that there is a trade-off. So it's not, you're not per se allowed, or you shouldn't use transformations, but you need to be a little bit careful. So what we saw is that if you get the convergence rate of estimators with respect to training samples and their error they gave, then raw data will converge to somebody. Any transformation might converge faster, but at infinity to something a little bit higher. Now, this is with infinite amount of training samples, which we don't have. So for a fixed amount of training samples, we're still better off in taking the transformed features, but at some point this might switch again. If you want to know more, there was a paper about this in last year's NeurIPS written by us. Finally, we want to answer the question on how to use this signal in a system. Well, we realized, based on the theoretical work we have been doing, that we can take the min overall transformation and it will work. And this can even be easily optimized. So just to illustrate how this would look like, if we have a data set like Yelp with a state-of-the-art around 0.25, then you can fire up expensive AutoML systems and get somewhere near the state-of-the-art accuracy. With our system, you get a very similar value in a fraction of the time. And this even works if there's some noise in the data. Again, here's the link to the paper. So these results are really promising, but there's still many unknowns with opportunity for research from our community, and that's where we need your help. So there are 2 major limitations. One of it being that how do we go beyond the base error rate? So base error rate has a clear limitation. That is a quantity which is with respect to the distribution, but it doesn't answer whether my finite data set is actually good enough. But if I would gather more data, that's the question we care about. Secondly, we know that training and test distribution might be different, especially if you use data augmentation or some weak supervision. The second aspect is we only care about accuracy as a metric for now, but users typically care about other metrics like F1 score, AUC, or robustness, or fairness. So there's a lot of exciting things that can be done here, and I'm happy to hear your thoughts about that. Over to Boehm.
Cool. So thank you, Cedric. Hey, everyone, I'm Bojan, and I'm a colleague of Cedric at ETH Zurich. And today I want to discuss sort of you can think of it as a follow-up question to the question that Cedric was looking at, and that is my data good enough? Does it meet the bar? And then the question is, if my data doesn't meet the bar, what should we do? Which specific issues of data we should focus on first? So that is the question we tried to answer, and that led us down the rabbit hole of ML data debugging, where we were working on designing a system called EaseML Datascope that could help us to answer this question. And obviously, this is an effort that involves a lot of amazing people, a lot of which are my colleagues and collaborators. So let's get back to the original ML workflow, which features a data set, and we have a model, and then we measure the model's accuracy or fairness or robustness or whatever measure we care about. And then we have some data problems. And not only that, but our data set is not small. It has potentially millions of examples. So it can be really challenging. So we just need to put our ML debugger hat on and try to tackle these issues. So the life of an ML debugger is definitely not easy, but they at least have the data quality dimensions that they could keep in mind. But keeping that in mind, the ML setting comes with additional questions that they may ask. What should I do next? Should I get more features? Should I remove some outliers? Should I get more data? Should I clean the data? So all of these options are sort of general categories of things we could do. But even when we decide which path we want to take, there's also the question of which data point we should focus on first, because there's only so many data points we can do in a single workday, right? So the first struggle is basically the huge and overwhelming amount of possible operations a data scientist can take. And secondly, of course, not all these operations are not equally beneficial. Some even hurt the performance, and some may improve the model. But the final problem is the usual ML workflow requires, once we make the interventions we want in the data set, we have to retrain the model and rerun the whole pipeline, and then observe whether we've done any good or not using our intervention. So yeah, our data debugger definitely needs some help. So prioritizing, so the question then becomes, how do we help the data debugger? So what could we offer them as help? And that kind of spun a whole sort of pursuit of ours. And there are two general directions, which will become more clear in the following minutes. But they focus on two general classes of data problems. The one type of data problem comes with the question of data cleaning, or which data examples should I clean? And the other one comes with the question of, are there some wrong values that are not easily detectable, but I want to remove or also fix? And so then with respect to these, again, utility measures that we care about, we imagine a sort of an importance metric, something that we can sort of allow the user to kind of order the data by some sort of measure of importance, and then guide their attention towards the data points that matter the most. And furthermore, our bigger dream is to not only allow this functionality of having importance that leads you to the goal, but also doing it in sort of real time, such that you don't have to wait for the whole feedback loop to end, but like hopefully that we're able to do it in an interactive way, such that the moment you make the intervention on data, you can immediately reshuffle those importances and then basically keep you as close as possible to some optimal data debugging path. Of course, this doesn't come for free. There are many challenges. In our ML training workflow, the question always becomes first, how do we even represent this importance and how do we compute it? So there's a lot of foundational work, which I'll mention in the following minutes, where people have been looking at different ways to define this sort of notion of importance. And the common thing about all of them is that it's usually pretty hard to compute these things. So doing it, a lot of times it's even intractable to do it in a sort of correct way, or theoretically correct way. The second issue is that a lot of that foundational work focuses primarily on a simple ML workflow that contains only a dataset and an ML model. But the majority of real ML code consists of actually a feature extraction pipeline. So keeping that out of our equations, we're actually sort of shooting ourselves in the foot, which we definitely should avoid. And finally, the question becomes how to really enable that interactive feedback loop. So doing it not only like making those problems not only tractable, but making it fast. And that's that's probably one of the hardest challenges. So then I want to just pause for a bit and just reflect on the existing work and what people have been doing in the sort of the pursuit to find different ways to guide people's attention towards data problems. And that in itself entails the question of what types of data problems are there, because different types of data problems may entail different solutions. So we recognize two sort of clusters of data problems, one of which we call missing values and the other we will call wrong values. I'll define them shortly. So missing values are something, for example, in a data where we have clear null values in a data set, or something that is easily detectable, for example, by using a simple SQL query that checks whether some sort of data validation query. So something that allows us to identify these things, and then each one of these missing values entails a domain of possible candidate values, which we can also pre-configure for our specific problem. But the challenge becomes then each one of these, and yeah, also then that's why we call these types of data sets uncertain data sets. The challenge becomes because each one of these missing values, we don't know which one is the correct value to select. So that kind of creates a space of training data sets, all of which could be filled in some certain way and clean in some sort of way. And that implicitly creates an uncertainty in the model predictions, because models can be trained on different versions of this data. And then we're uncertain in the prediction. So that's the sort of the quantity we're looking at is the uncertainty of the model. And how do we define importance in order to guide the user to clean their data in a more efficient way? So people have been looking at it, of course. One paper they want to highlight is Active Clean that used gradient-based methods to guide the search of the user. And another paper that is from our group where we use information theoretic methods to compute, to express importance in terms of entropy reduction. So just as an example of the question of whether this type of importance does even help us to be better than just blindfolded randomly picking data points to clean. And as we can see, it shows some promise. So it is possible, for example, in certain situations to clean only 50% of the data and close 80% of the accuracy gap. However, there are some problems that still remain. So the speed is definitely still an issue. And also a lot of these efforts don't support real end-to-end ML pipelines. So that's an open, sort of an open thing. Furthermore, I want to talk about the second category of data errors, which I call here wrong values. And I simply distinct them by the fact that they're not possible to detect with a simple SQL query. So you saw also in Felix's talk where he was talking about these data errors, which are basically, a lot of them just need human attention to look at them in order to decide. There's no other way to decide whether the data is wrong or not. So the question is, can we help the human find those data points? And yeah, we call this an incorrect data set. So these data points or these wrong values definitely contribute to quality drops. And then the question is, how do we guide the attention? So one way that people have been looking at it is through the use of what's called an influence function. That's another gradient-based method, and it's received a lot of attention in the community. Furthermore, there's also a sort of a game theoretic method called Shapley value, which our work is also based upon. And as we can see, another sort of test whether sort of this type of importance helps us. And as we can see, we again are able to arrive faster at closing our accuracy gap, as opposed to just being sort of going about it randomly. And of course, the problem still persists, not fast enough and no pipeline support. So then the question is, how do we define these? How do we actually apply these notions of different ways to define importance? How do we apply it to real world scenarios? And also that dreaded speed, can we make it better? So our approach there is to kind of pick into both bags of tricks. We are just going everywhere and just finding in database community and ML community, whatever we can find. And then we basically try to assemble some sort of proxy solution that would be good enough to be close enough to reality, but still computationally more efficient. So the elements of this proxy approach are three heuristics that we apply. The first one is to represent training data sets always as COD tables. This just means that different wrong values, we assume that they're not correlated with each other. Secondly, there is the heuristic of representing feature extraction pipelines, which in principle can be arbitrary code. We approximate it using SQL queries. that allow us to leverage a lot of knowledge from the database community to do a lot of sort of computational efficient tricks. And thirdly, and sort of most significantly in terms of speed, is the KNN classifier. So as opposed to pretty complex ML models, the KNN classifier is very simple and allows us to do a lot of algorithms pretty efficiently, as you will see. So, and then based on that, we compute the importance with respect to the measures we care about. So what do we achieve then? Well, compared to the general classifier, if we don't use the KNN thing, then a lot of these problems by definition are in the sort of Sharpie hard space. However, by using the KNN classifier, we're able to reduce a lot of the scenarios that we care about to polynomial time, and also some of them we can bring down to being as fast as basically sorting the data. So let me quickly show you just one sort of example scenario of a dirty data set where we have wrong labels. And we have, you know, the ML model or ML pipeline actually, and then we observe problems in our accuracy. And the question is, can our Shapley value importance help us in guide the search? And keep in mind that for a reasonably sized data set, this is not still, we're still not at the million scale, that's the dream, but this is still a decently like average sized data set where we're able to give answers in seconds for any single query. So, and as we can see, yeah, we managed to perform it faster than being random. So just to give you a glimpse of the sort of the space ahead of us, as we see it from this perspective. Well, there are two things that we want to, or that we were thinking of looking at. One is, and both involve things that we don't actually know about, and there are some things we want to build, but we also don't know all the details. So the first one is, how do we go beyond additive utilities? And accuracy is an example of an additive utility, but other utilities, for example, fairness, our KNN-based Shapley method seems to fail at there. So there's some sort of theoretical gap which we need to close to make this actually work. And as we can see here, we are actually not that much better in random with respect to fairness. On the other hand, there's another thing that kind of puzzles us. Can we actually go beyond data importance? Can we try to apply this sort of importance notion to other things such as pipeline operators, for example? And the dream then would be to kind of be able to debug your Jupyter notebook with respect to some sort of metric, for example, fairness. You can check which operators in your code are contributing negatively or positively to the metric we care about. So this is a project we're passionate about, but still in very early stages, we don't understand a lot of the things. So definitely we need help. And so to conclude, we talked about the whole sort of space we've been looking at in our group, and primarily focused today on the sort of the data cycle. However, there's a broad area to be discovered here. This is just a small piece, and that's why we're basically very excited to participate in this workshop, to be able to maybe spark some collaborations and enable a lot of the questions being answered in the future. Thank you so much.
Okay, great. Thank you very much. So now let's take some questions. So Felix, if you have a question, also speak up, right?
Sure, I'll just start and speak up. So thank you for two very excellent talks. I mean, I almost feel stupid in giving this introductory kind of talk, and then you guys are already halfway towards the Holy Grail. So this is very cool. I'm very impressed. So I think I don't really have a specific question, but I do have one thing to add, maybe as a guide for the whole community in the future, is really what I also said in my talk, to consider these, let's say, non-computer science-y dimensions. I think this is important. I mean, we do work with a lot of folks from industry, and so I always take away two things. One is they need everything to be very simple, right? So they want to understand what's going on. They can't use too fancy things. And the other thing is they need arguments in their organization, right? They understand the science, they understand the need, but they need to show why this is cost effective. They need to show understandability, these kind of things. So these non-tangible things we need to keep in mind somehow that's very difficult, and it's not a VLDB paper to to address these things. But I've seen that in practice, if we want to have impact as a community, we need to take care of those as well. So thank you very much, both of you, for the talk.
Thank you.
Yeah, thank you for the comment. Yeah. So for this one, essentially, and we draw this very beautiful picture, but it's really the overly simplified version of the real world. And even for these two data cleansing problems, I mean, there are more things we don't know than this little small corner that we have some knowledge about, right? So there's more like a cry for help about like how should we deal with this, right? Instead of that we get a solution out of this, right? So, okay, great. So we have one question online, right? So can a human really generally fix wrong values without coming back to the data collection phase? So Bojan, I guess that's a question to you.
I mean, that is, I mean, it's an assumption. We always have to make assumptions that it is possible to clean the data with enough, I guess, research or with enough time. Sometimes we may want to throw away some data. So if data is too dirty, we don't know what to do with it. Maybe we want to throw away, we want to get new data. So this sort of data scope approach was to kind of try to answer that question of also the original conversation started with data evaluation. So with acquiring more data was also the original question. So things like Shapley value can help in the acquisition process. But if we cannot clean, then I don't know. We guys have to throw it away. I don't know.
Great. Is there any questions from the local audience? Okay, great. Let's thank our speaker. And then let's start to our next keynote speaker. So Cedric will moderate.
Thanks so much.
Thank you.
Bye, guys.
All right. So our next speaker is Matthias Boehm. He's a professor for data management at TU Graz, working on Apache SystemDS. And previously, he was with IBM Research Almaden, working on Apache SystemML. Matthias got his PhD from TU Dresden, and he has won several awards during his career, most notably the 2016 VLDB Best Paper, the 2016 Research Highlight Award, 2016 IBM Pat Goldberg Memorial Best Paper Award, and just this year, the Sigmod Data Science and Engineering Best Paper Award. And we're pretty much looking forward to your talk, Matthias, which is going to be about data independence in ML pipelines and data science workflows.
Awesome. Thank you so much, Cedric. And thanks for having me at this awesome workshop. So we already seen a couple of very interesting talks, especially on data quality. And I will make the case that in increasingly composite machine learning workflows and data pipelines, data independence is of crucial importance. So we already have seen that example that normally we start off with some model training, and historically we paid a lot of attention to how exactly we craft those algorithms, how we distribute them, how we place certain operations, and then ultimately we perform some model scoring. Now, more and more we view them as kind of abstract primitives and wrap them into functions. So there's some existing off-the-shelf library function for training and prediction. Usually, of course, there is some form of feature transformation data preparation. So we might apply a dictionary-based encoding, one-hot encoding, binning, feature transformations like that. Now, in order to get good accuracy, we should not underestimate the power of hyperparameter tuning. If we tune a lot of hyperparameters, we should probably apply cross-validation. And essentially, we wrap those core library algorithms into more and more outer loops for hyperparameter tuning and essentially AutoML, so model and feature selection. And I think data-centric AI is a great topic for such a workshop, because there are indeed a ton of additional problems. And the way I see that is as additional loops around those core machine learning pipelines. So we have essentially an additional enumeration steps for data programming, data augmentation. We apply different shearing and kind of transformations with various parameters, and we again tune hyperparameters for those individual parameters. On top of that, we have data cleaning and essentially try out different primitives and evaluate what these signals or what's the impact on the machine learning application. In addition to that, and we've already heard a little bit about debugging, we want to have tools that allow us, and this one example from our group is SliceLine, that allowed us to find the top k worst data slices as conjunctions of attributes, where the trained model performs significantly worse than on average. Now, this kind of debugging information can now be fed back into, for example, our enumeration of data cleaning pipelines, where we might want to focus exactly on those data slices where we see a lot of errors, because there any fixes of the data could have potentially more impact on the trained model. So ultimately, what we see currently is an increasing hierarchy of composite primitives of library functions, which makes it increasingly hard to actually go to the inner machine learning algorithm and place them onto a GPU, place them explicitly into a sparse representation. So just to elaborate a little bit on dimensions we're seeing, so on the one side, there are plenty of different data representations, so dense, sparse, compressed, dedicated graph data structures. And what we see really in machine learning, but also systems conferences, is that sparsity exploitation is the mega trend. And it really ranges from the algorithms, how we have sparse connections, all the way down to the hardware, how we perform clipping and essentially convert it into dense operations. Second, data placement. So as we have those hierarchies of primitives, it becomes increasingly hard to apply global placement where we place all the operations on the GPU, because some operations are simply not amenable to those kinds of computing devices. So it's about local versus distributed operations, CPU, how we ensure or exploit our non-uniform memory architectures, how we use FPGAs, and increasingly also ASICs in that mix. Furthermore, there are more and more specialized data value types that have different trade-offs in terms of precision, but also range. This is really of crucial importance for certain accumulators, for example. And finally, and I took this from the Ludwig paper, there are just many different data modalities and respective encoders. Now, also dimensions are not independent. So depending on the data types, we actually implement operations differently, and we might want to place them differently. Given those different dimensions, together with the increasing hierarchy of machine learning pipelines, is an extremely challenging problem. So in this talk, I argue for a very old concept, and this old concept was 50 years ago, which is data independence. And it's literally a quote out of Ted Cott's paper, data independence referring to the independence of application programs from the growth in data types and changes in data representation. So I argue, as we currently see more and more specialization, that data independence and finding the right abstractions is of utmost importance. So how we do that in systemd, which is the system I'm working on for the last decade, is essentially via abstract data types. So we encoded machine learning algorithms in a high-level domain-specific language with R-like syntax. So in this case, we're reading kind of input matrix from distributed file system, compute an initial gradient, and then until we reach a target norm, essentially compute conjugate gradients and update our model accordingly. So the crucial takeaway here from those kinds of scripts is that we work with abstract data types. So nowhere are we encoding, this is a sparse or dense matrix. Nowhere are we encoding, this is a distributed matrix. And essentially let the optimizing compiler infer shapes and reason about costs and memory budgets, and then automatically compile essentially appropriate hybrid execution plans. And that leads us to a separation of concerns where people can focus on the individual algorithms and other people can work on the actual underlying compiler and more infrastructure-oriented topics. And that really frees a lot of resources. We're not having to pre-optimize different library versions for different deployments. And as you've seen, it's so many different dimensions and they are not independent, which leads to an exponential cube of essentially combinations of things. So we take those scripts in systemd and essentially an optimizing compiler compiles hybrid runtime plans that are composed of local in-memory operations and distributed operations on a data parallel platform such as Apache Spark. So the project was started as SystemML at IBM 2010. I joined in January 2012 and then really worked on it almost for a decade now. And the interesting observation is as we wrote algorithms on top of that, the underlying technology stack changed. So it went away from MapReduce to Spark, starting in the mid-2010s. Essentially, GPU became much wider use because of increasing workloads that contained deep neural networks. But the key takeaway is as the technology stack evolved, none of those high-level scripts had to change because the optimizing compiler could simply rewire it to different execution plans. And with that, you have a protection in the investment into those primitives that you're building in script-based languages. So when I then joined Theocrats in 2018, we essentially forked SystemML and tried to build, increase the scope to end-to-end data science pipelines and essentially supporting data quality, so data cleaning, data preparation, and yeah, the end-to-end data science lifecycle better. Later, it was merged back into Apache SystemML and essentially renamed to systemd. The compilation of distributed, so hybrid runtime plans of distributed operation and local operation is the first example of data independence. In the rest of the talk, I would give you some additional examples of data independence where it worked out very well for you and potentially inspires you thinking about the right abstractions. So first, a little bit of the architecture. So systemd, many users come through various APIs, including the new Python API. Then there's this optimizing compiler applying a lot of different general purpose optimization passes, but also very specific optimization passes for simplifying linear algebra expressions and entire conditional control flow programs. Then you have a core control program that runs the main conditional control flow and orchestrates a number of components such as a buffer pool for eviction of intermediates, various IO components, and the individual runtime instructions where we have essentially 40 different operations, different implementations for local CPU, GPU operations, but also data parallel Spark operations and now new federated instructions as well. So this building this up really took a decade, and what we are proud of is a huge test space, which now actually helped us to make it mature enough that you can build up an entire hierarchy of abstractions, built-in functions that are themselves based on our DSL, and with that essentially create those composite machine learning pipelines, and let then the optimizing compiler collapse all those abstractions and optimize it jointly the entire pipeline. All right, so the first example is lineage. So in order to ensure reproducibility, we provide means of fine-grained lineage tracing that allows you, so we build up as we execute operations, essentially lineage traces, capturing all the non-determinism like system-generated seeds. And given the same data and the lineage trace, you can actually reproduce exactly the same intermediate. There are lots of individual challenges how we deduplicate those traces for loops with different control branches, for example. But a key observation is, since we can uniquely represent an intermediate by its lineage trace, we can use that as a key in a cache and essentially reuse intermediates, which are increasingly common in those complex machine learning pipelines. So one example is here we have a basic grid search over a linear regression model that takes different regularization parameters in. So at the surface, it looks like, we can't reuse anything. But letting the optimizing compiler collapse those abstractions, you see that the core matrix multiplies, they are equivalent and independent of the regularization term, and you can automatically, under the covers, actually reuse them. Furthermore, if you're in feature selection workloads, there's plenty of potential where by adding additional features, we can reuse partial intermediates from previous iterations and only create compensations for the additional features. So that's the second example for data independence. We are currently in the process, or for years in the process of extending our lossless matrix compression framework that also allows us to execute linear algebra operations directly over the compressed representation. So what you can imagine is if you have a small number of distinct items, you're essentially creating a dictionary, and in dense dictionary encoding, for example, you encode the individual values at the position in the dictionary. And then certain operations like the maximum, for example, become extremely fast because you only apply them over the dictionary, but you can also apply directly matrix multiplies on this representation, and with that change the asymptotic behavior. Now, in this latest work, we essentially focus on workload-aware compression, where we want to make it much more generally applicable and even generalize this trend of sparsity exploitation to general redundancy exploitation. So if missing value imputation introduced a lot of common values, then compression gets completely rid of them, but you can ensure correct results. Now, in this workload-aware compression, what we are doing, we first summarize the remaining linear algebra program, as in what kind of operations will we execute over it, which then inspires how we compress this matrix. And then in turn, once we know how it's compressed, we essentially can change how we generate execution plans, because if we compress it down, certainly it fits in memory and we don't need to compile distributed operations. So third example of data independence. The fourth example is federated learning. So federated learning in general tries to learn machine learning models without central data consolidation for privacy concerns, data ownership, for example. You can do that, you initialize, so in a traditional pyramid server or a similar distribution strategy architecture, you can initialize a model, send it to all the workers, they make a forward pass, backward pass over your neural network, for example, to compute gradients, and you only exchange those gradients, so aggregates. We support, in general, really federated linear algebra and federated parameter servers, so both of them. And the way we integrated it is that we introduced new metadata objects for federated matrices and frames, which allows you to say this logical matrix is composed of individual row partitions or column partitions that are located physically at those federated sites, and you have the IPs and ports where there are servers on the other side listening for you to send requests to. And then really the coordinator runs the linear algebra program. As soon as an operation hits this metadata object, it simply forwards, okay, this part of the matrix is on this particular worker. You then compose, for example, a matrix vector multiplier over a row partition federated matrix, become many small matrix vector multiplies and yielding again a federated vector, but you can also then pull this vector because they are aggregates already. Now, we ran over quite a variety of different algorithms, including traditional machine learning algorithms, unsupervised clustering, dimensionality reduction, and neural networks in local area and wide area networks. So one of my PhD students ran the coordinator in Copenhagen, Denmark, and all the federated workers were here in Graz, Austria. And we see a very moderate overhead, which is makes it absolutely practical to apply. Now, the local baseline is also competitive. So systemd-s is certainly in the same ballpark as scikit-learn for traditional algorithms and TensorFlow for neural networks. And essentially what it allows us is to avoid re-implementing all those different algorithms for federated operations. Simply the compiler compiles them to different things, and you have one primitive for a machine learning algorithm that's simply deployed in different ways. Federated learning is also largely related to data and task placement onto multiple different devices. So in the Daphne project, we try to build an open and extensible system infrastructure for integrated data analysis pipelines, which is directly in topic for data-centric AI, together with quite a number of great partners, including ETH. So here in those pipelines, we want to support machine learning, data management, query processing, but also simulations and high performance computing, which are increasingly supported by machine learning as well. So we have a lot of those machine learning assisted simulations. Now the core principles is that that also 3 different areas actually can be expressed in frame and matrix operations, and in order to compile it into hybrid execution plans fully utilizing heterogeneous hardware, key is really data independence, and we want to build an extensible infrastructure. So in terms of multiple devices, the concepts that you've seen for federated learning directly apply here to multi-device placement as well. So you have a matrix or frame that is physically partitioned across devices. So instead of just placing an operation on an FPGA or GPU, you can say, well, my GPU is 2.5x faster, so I place 2.5x the data onto the GPU to fully utilize all those different devices, which is of course a hard problem for complex stacks of operations with different characteristics. And then we essentially compile fused operator pipelines where we take chunks, morsels of the input and essentially feeding them through entire compiled pipelines. How we compile them, Daphne is an MLIR-based compilation stack, and so the multi-level intermediate representation that ultimately compiles down to really LLVM execution plans. The core challenge is, in Daphne, we want to support sideways access into this compilation chain and allow that really extensibility, that people can come along with their new kernels, new data types, and we have the right abstractions to incorporate those new types without much overhead. All right, that brings me to the end of my talk. I have 3 parting thoughts. So I'm strongly convinced that data independence is of utmost importance as we build up those more and more complex machine learning pipelines, including data-centric AI, and we call it integrated data analysis pipelines that have many different aspects of pure processing, machine learning, all the way to high performance simulations. Second, we're just about to, together with Doris and Baruma, tomorrow we are actually submitting the new DEAM workshop. And given the current introduction of the scalable data science tracks and data science and engineering tracks at Sigma VLDB, we are kind of thinking about modifying and evolving DEAM a little bit. And the way how we do that is by introducing a new paper category for applications and tools that allows you to actually provides a forum to share use cases, data sets, benchmarks, more visionary ideas that are not fitting very well currently in other kind of paper categories. So we're more than happy if you have topics related to data-centric AI, that's the perfect place to submit it there. And the final thing is really more of a perspective. So there was this great keynote by Phil Bernstein on schema mapping and matching back in 2007, where he reviewed very nicely, essentially, the previous 7 years of schema mapping, lots of papers published in the space. And it was a very interesting question of, despite all those tools, why is it still so labor intensive to develop engineered mappings? And the conclusion was because of unavoidable consequence of ambiguity. Which then inspired essentially this model management 2.0 and new primitives that recognize that on the one hand side, the semantics are very weak, but you have to really precisely engineer those mappings. I believe data-centric AI and really complex integrated data analysis pipelines have a similar characteristic, that often these semantics are weak and it's hopeless to fully automate it. So I would encourage everybody to think about and build tools that ultimately augment essentially data scientists, machine learning researchers, and domain experts in a semi-manual manner in order to really ultimately help them to reduce the manual effort. with that, thank you so much. That's all I have. And I'm happy to take questions.
Thank you very much, Matthias. Very nice talk on how to achieve data independence, how to build new systems and what is needed for our community. Very inspiring. So I have one quick question and then probably maybe one of the audience, and then we'll probably move on to the next talk. So you were talking about one motivation being multimodality. I didn't see it yet touched. So how do you plan to incorporate that into your system, or what's your thought on that?
That's an excellent question. So right now I don't have a good answer for that, but you can certainly, so that there have been other tools like Overton and Deep Dive that essentially from the beginning said, no, don't reason about algorithms, reason about features and make that the central abstraction and automatically enumerate essentially different algorithms that can deal with them and different strategies. So I think ultimately, and I'm saying that for the last 10 years, it's always about the optimization objective, how we precisely define that. So if I want to have something that reasons about modalities, different representations, it's somewhat in the multi-objective space of saying we at the same time affect accuracy and runtime. Right now, we are very moderate and we say, let's first fix the simple problem of given a fixed algorithm and a logical algorithm and accuracy, how can you optimize under the covers runtime for fixed accuracy? And the other is just even more complex and has more degrees of freedom. Yeah. But absolutely, I think it needs to go in that direction. And we need to think of good abstractions, how to allow people to automatically enumerate different representations. Yeah.
All right. Yeah, that makes perfect sense. Yeah. Any question from the audience? Good. So let's thank the speaker again, and then we can move on to the next talk. Thank you very much, Matthias. All right, so next two talks are going to be by amazing PhD students we have here at ETH. So the first talk is going to be given by Gregor and Lorenzo, which are both PhD students in the data analytics lab supervised by Professor Hoffman. And they're pretty much interested in the theoretical aspects of deep learning, aiming to obtain insights on the inner workings of deep models. With that, I give you the stage.
Hi, can you hear me?
Yeah, works.
Okay, thank you. Thanks for the amazing introduction. All right, so hi everybody from my side, and welcome to the presentation of our work titled Disentangling the Roles of Curation, Data Augmentation, and the Prior in the Cold Posterior Effect. As the title of the paper already alludes to, we're going to discuss several factors in deep learning pipelines that have a tremendous impact on the performance of Bayesian neural networks. Here we will focus more on the roles of data curation and data augmentation, since these two are very relevant to the theme of this workshop. If you, however, want to learn more about the role of the prior, check out our paper or send us an email. Now let us start with a brief introduction to Bayesian neural networks, or short BNNs. On the left side of this picture, you can see a standard neural network trained by SGD, where each weight is simply characterized by one value. On the right, you can see a BNN, where instead of having only one value, we associate an entire probability distribution to each weight. How do we do this? First, we choose a prior distribution for each weight. This is usually a very simple distribution, such as a Gaussian. We then specify a likelihood model that describes how the output of our neural network behaves. The goal is then to obtain the posterior distribution of the parameters, which incorporates the knowledge we have from the training data into the parameter distribution. We do this by using the famous Bayes rule. However, in stark contrast to the usual textbook examples, we cannot obtain the posterior in closed form. In practice, we hence have to resort to approximation schemes such as SGM-CMC or variational inference. But first, why should one use BNNs instead of standard neural networks? One reason is that BNNs naturally consider a multitude of solutions and integrate over all of them. This produces a more robust model that is less keen to overfitting. Another reason is that BNNs are actually backed by proper theory, which makes them more principled compared to gradient-based neural networks. Finally, BNNs allow the practitioner to assess how confident the model is on a given prediction, which is obviously quite beneficial for safety-critical applications. While definitely advantageous on paper, BNNs also come with some issues. As already mentioned, obtaining a closed form solution for the posterior is intractable, and approximation methods need to be employed. One such method is SGMCMC, where one defines a posterior energy function, which we show here. This function is then used as the potential in the Langevin dynamics shown here on the slide, which is then simulated to produce samples from the posterior. Using those samples, we can then perform Monte Carlo approximations for the final predictions. Now, the details of this method are not so important for this talk. The key takeaway is that running this method is extremely expensive, even compared to standard neural networks. But what is even worse and more concerning is that in practice, BNNs often underperform SGD solutions. There exists, however, a very simple and kind of mysterious trick. Simply scaling the potential energy that we saw before by a factor of 1/t, where T is usually called the temperature. And we see in practice that this can boost the performance dramatically. So what is observed in the literature is that using so-called temperatures that are significantly smaller than 1 result in a way better performance, even beating the SGD solution by a large margin. Here we show the performance of a ResNet on CFAR 10. And indeed, the best performance is usually observed for T way smaller than 1. This simple trick begs for an explanation, and this is what we set out to find in this work. It turns out that data curation and augmentation can play a very critical role. Lorenzo will explain this now in more detail.
Thank you. So we have three main hypotheses here, namely consensus theory, data augmentation, and bad prior. However, only the first two are relevant for this workshop, so we will focus on them. So consensus theory, interestingly, attributes call posteriors to the data is collected. And this idealized theory of consensus says that essentially we have S labelers that label independently each image, and the image is added to the data set only if all the labelers agree. The theory then establishes a nice correspondence between the number of labelers and the inverse optimal temperature. The intuition here is that each data point is labeled S times, so the likelihood should be S times stronger. Then we have data augmentation. This hypothesis states that by using data augmentation, we are adding extra data points to the data set that are not taken into account in the likelihood model. This can be seen from the likelihood model, where we assume exactly n data points and IID data, and both these assumptions are broken by data augmentation. In this sense, cooling the likelihood is justified as it is equivalent to overcounting the data points. But let's go to the experiments, and essentially for the experiment, we use SGMCMC to sample from the posterior with cyclical step size and momentum, as in the original paper on cold posteriors. And our experiments show that when data augmentation is turned off, there is no cold posterior effect. And this is surprising from a consensus theory standpoint, as both SVHN and CIFAR 10 undergo a curation procedure. But our interpretation is that these datasets might undergo a milder form of curation than the strong curation argument described by the consensus theory. However, we then devise an experiment where the role of the labeler is played by a classifier trained on part of the training set, and then S copies of the labelers are used to simulate the consensus theory. In this case, we see that the CPE arises, confirming that strong curation can indeed cause the cold posterior effect, but in practice, probably mild curation is used. Now let's go to data augmentation, and we are able to show that data augmentation in fact causes the CPE in both CIFAR 10 and SVHN for standard augmentations. And this confirms our intuition that extra correlated data points are not taken into account in the likelihood model. Then I have added an extra slide to show some ongoing research. And essentially here we use group convolutions to design a model that is a priori invariant with respect to the transformations. And in this case, adding these extra data points does not add new information for the model. And the optimal temperature is 1, as you can see on the right. On the contrary, if the model is not invariant, then we have a strong cold posterior effect on the left. In other words, the optimal temperature correlates with how much the model is invariant with respect to the augmentations. And now, therefore, we are trying to study cases in which the optimal temperature can be computed before training. And this can save a lot of computational time. So just to recap, we have shown that there can be many causes to this CP, it's called posterior effect. And so it's not a quick fix. But in particular, many tricks that are used in deep learning, like this augmentation, must be dealt with in a more Bayesian way, so to speak. Also, strong dataset curation might affect the practitioner that builds the model. Therefore, we encourage researchers working on data collection to detail the way the dataset is curated in their publications. Finally, we also deal with the prior and show that also bad prior can cause a CPE, but this was not really part of this talk. Thank you for your attention, and I'm happy to take any question.
Thank you very much for this very interesting talk in how to bring some theory behind what people have been doing basically for years. So if I understood correctly, so you understand which temperature you need to scale in based on a prefixed data augmentation method or labeling strategy. Could you use your method to suggest better data augmentation or labeling strategies?
In a sense, yes, because if essentially, let's talk about data augmentation. If you know that your model is already invariant with respect to those augmentations, then the augmentations are useless. And so essentially, this temperature tells you that optimal temperature equal 1 tells you that you shouldn't use these augmentations. On the contrary, if you experience this cold posterior effect due to data augmentation, you know that essentially you are not invariant with respect to these augmentations. And so this optimal temperature, in a sense, is a measure of invariance with respect to the augmentations, let's say. So we are working on this right now to better quantify, like, what's the optimal temperature with respect to how much the model is invariant, let's say.
I see, makes sense. All right, thank you very much. And with this, we move to our next speaker. The next speaker is Lukas, which is currently a PhD student at the Applied Cryptography Group. And he's also a member at the Privacy Preserving Systems Lab. So his research focuses on data privacy, systems, and applied cryptography. And we're pretty much looking forward to what you have to say. Go ahead.
Great. Can you hear me? Is all good? Yeah.
Yeah, it works. Thanks.
Oh, perfect. Thanks for the introduction, Cedric. So hi all, my name is Lukas, and today I'm going to talk about our work on robustness in secure federated learning. This is joint work with Hide, Alexander, Nicholas, and Anwar. So to train a machine learning model, a service typically collects all user data within a cloud infrastructure in a single location. This raises both privacy but also liability concerns. To address this issue, decentralized learning has emerged as an alternative way to train machine learning models. So decentralized learning is a machine learning paradigm that enables a party to train a machine learning model without the need to have direct access to training data of participants. There are different flavors of decentralized learning, such as federated and collaborative learning, that differ in how information is exchanged and potential deployment scenarios. In this talk, the focus is on federated learning. So let me give you a brief overview of the protocol. So federated learning is a round-based protocol that allows the server to train a machine learning model using data that is scattered across a large number of participants. In each round, the server selects a subset of the clients and broadcasts the global model. Then the selected clients train the model on their local training data. And finally, the client sent their model updates to the server, which aggregates them into a global model. So to protect the privacy of sensitive client updates, a federated learning deployment typically also employs a secure aggregation protocol, where the server only lands the aggregate of updates, but not the individual updates of each client. In this talk, the focus is on the challenge in robustness in federated learning. Besides that, federated learning is susceptible to known security and privacy issues encountered in the typical machine learning setting. Federated learning is exposed to new attack surfaces affecting robustness. First, compared to the centralized setting, federated learning exposes the training process to a multitude of participants that potentially can be compromised by an attacker. As a result, an attacker can try to integrate malicious behavior, as for example, a backdoor into the global model. Next, an attacker that controls a subset of clients can observe and influence the model behavior over multiple training routes. Further, not only they can alter the local training samples, but also manipulate the model updates, which amplifies the effectiveness of robustness attacks. Lastly, secure aggregation prevents the coordinator from inspecting or auditing the model updates of clients. So in our work, we are interested in understanding the impact of these robustness issues in more detail and design new systems that enhance the robustness in secure federated learning. In this talk, I highlight some of the high insights that we obtained in our robustness analysis and give a high-level overview of our system ROFL that enhances robustness in secure federated learning. So forth, there has been a flurry of work that exposes vulnerabilities in federated learning. In our analysis, we aim to demystifying the inner workings of existing attacks and providing some technical insights about federated robustness in practice. We showed that existing attacks mainly target two characteristics of the federated learning pipeline: the aggregation rule and the capacity of the model. While the effectiveness of attacks on the aggregation rule can be reused with more robust aggregation mechanisms or client update constraints, attacks against the capacity of the model are hard to defend against and involve fundamental trade-offs with other characteristics of a model. So first, let me show you how a single attacker can integrate a backdoor in a single training round by attacking the aggregation rule. The attacker embeds a malicious behavior into the model by training the model on poisoned data. In this example, the attacker's model misclassifies images of cars with vertical stripes on the background wall as birds. Once the malicious model is crafted, the attacker simply scales the model update to override the other participants in the aggregation. Here you can see the severity of such an attack in one of our experiments. By attacking the training algorithm in a single round, the attacker is able to integrate the malicious objective into the global model, while the accuracy on the nearly remains the same on the main task. This is a severe and also practical attack, since an adversary only needs to compromise a single participant that it is selected in a single round. To reduce the risk of attacks targeting the aggregation rule, the server has to employ more robust aggregation mechanisms. In the centralized distributed learning setting, there exists a large body of research on Byzantine-tolerant learning algorithms that are robust against Byzantine clients. However, they are not directly compatible with secure aggregation. These rules often employ non-linear logic that are not efficiently implementable in secure computation with large input vectors. So an alternative approach is to enforce constraints on client inputs. In our analysis, we show that a norm bound can be sufficient to prevent attacks that rely on scaling for success. Due to limited time, I will not show this result in this talk, but please check the paper if you are curious. Another vulnerability that an attacker can leverage is the capacity of the model. Model datasets often follow a classical long-tail distribution, such as a SIF distribution, as depicted here. A significant fraction of the dataset consists of rare, noisy, and atypical samples located at the long tail of the distribution, as for example, these bus images from an unusual angle. It has been shown that large over-parameterized deep learning models tend to allocate a large part of their model capacity to memorize these sparse long-tail samples to achieve good accuracy. Model memorization in relation to data privacy has been explored in depth because memorization can reveal sensitive training data. However, the question here is, does it also affect robustness? And we observe that it can, because an attacker can select rare long-tail samples as a backdoor target. Intuitively, based on this observation, these targets are easier to be integrated into the model as the model tends to memorize these noisy samples. In this example, the adversary tries to misclassify European sevens as ones in the MD's dataset, which mostly contains of American handwritings of sevens. Hence, these European sevens belong to the long tail of the distribution. We assume that the norm bound is enforced and the attacker can only marginally scale the update. In this scenario, the attacker can successfully integrate the tail backdoor, although more robust aggregation rules are used. Update scaling is not necessary for access. The adversary just needs to participate in the training process long enough. So preventing such attacks entails to suppress the learning of these long-tail data samples. This can be achieved with methods such as noise addition on gradients or update compression techniques. These countermeasures, however, introduce various trade-offs with respect to accuracy, privacy, fairness, and robustness. Hence, defending against such attacks is challenging and goes beyond just robustness issues. The trade-off between these characteristics is still poorly understood and requires further research. So to conclude, federated learning robustness is an open challenge. However, update constraints such as a norm bounds can be a first step to reduce the risk of the most critical and practical attacks that we showed at the beginning. With ROFL, we introduce a federated learning framework that integrates secure aggregation, but still allows the server to enforce constraints on model updates. In particular, ROFL uses zero-knowledge proofs to enable the server to verify constraints on the client's updates without actually inspecting them. Using zero-knowledge proofs on high-dimensional updates raises various scalability challenges, which we address with various optimization on the machine learning, but also on the cryptography layer. With that, Roffle can achieve up to 6x performance improvements, both in computation and bandwidth on known constraints, which actually enables the framework to train practical models. So with this, thank you for listening. If you're interested, a preprint of the paper and the code of the framework are actually available online under the listed links. So thank you.
Thank you very much, Lukas. So amazing talk and very nice viewpoints on privacy and security aspects on machine learning algorithms. So I have one question, and so you focus pretty much on attacking and offering certificates for existing machine learning algorithms. Could there also be ways to design new algorithms which are in themselves already somehow secure and private?
Yeah, for sure. This would be one path to go, right? Instead of using just standard SGG and aggregating the gradients, you can look into how to do this more privately and with more robustness. But I think it's very challenging because there are various robustness and privacy somehow also conflicting with each other a bit, right? So there are various trade-offs that you have somehow to decide on in these distributed learning algorithms.
Definitely, yeah, this makes perfect sense. And so to highlight this trade-off to the user, so what's your approach there?
So to the user, yeah, I mean, in the end, you want to do federated learning because of privacy, right? So you don't want to reveal the training data to the server itself. You want to keep the data local. So I think privacy is one of the most important parts, right? So you need to ensure that the user data remains private, but still you can ensure certain robustness guarantee for a service. So in my opinion, privacy is the most important factor in these pipelines to even make sense of federated learning or distributed, decentralized learning. Yeah, but yeah, I think showing this to the user is a challenging thing. So it should be by default not revealing the data of the user, right? So this should be somehow the highlight of it. Yeah.
Okay. Yeah, makes sense. All right, thank you very much again, and let's move on to the next talk. So our next speaker is going to be Debojyoti, joining from the US actually. He's a VP engineer and leads AI Ops and the other AI ML efforts at Nutanix. So prior Nutanix, Debo was a visiting scholar at Stanford, a distinguished engineer at Cisco Systems, and he was also a postdoc at USC, where he also did his PhD. One second.
Hi, thank you for the warm intro. I think I can't share the screen. Somebody's sharing.
Now it should work.
Okay, thank you.
All right.
Hi. So I'm going to talk about something slightly, more industry oriented and less. It'll appear to be less researchy, but hopefully we'll come back to some of the deeper research questions towards the end. So let me just share my. Come on. Yeah. Okay. So yeah, a little about me. A little about me that was not covered in the intro is that I lead a bunch of AI/ML efforts inside Nutanix in addition to AI Ops. And for those people who don't know, Nutanix provides a hybrid cloud platform, consistent platform with class-leading storage. So we'll get back to the storage part and how it's relevant to data-centric AI. So let's actually look very quickly because we don't have much time over here. So essentially what's happening in the industry today is if you look at the enterprise comes in all shapes and sizes. You have like very advanced enterprises like Google, Facebook, and any of the newer unicorns and public companies that you see. And then there's this long tail of the traditional enterprise. And in traditional enterprise, things have been optimized for decades or even maybe a century or so of business processes where things have been optimized based on business data, but it's been kind of much more manual than automatic. So the first thing that's happening, because of machine learning, there's been a huge transformation happening in the traditional enterprise. And it's because of, you've heard it all, right? There's been a huge amount of data explosion. People are like collecting more data in the enterprise, whether it's from cameras or whether it's even in the, people are even doing farming with data-driven approaches. And there's just lots and lots of data. That's a real problem for the traditional enterprise, because while the traditional enterprise is trying to digitize itself, so it's called the digital transformation, you'll hear these buzzwords. Essentially, it's trying to collect, manage the data, and convert it into insights with AI, and that helps them take business decisions or actions. And AI is accelerating the digital transformation by providing learned insights, which we all know. The key challenge that we see in the traditional enterprise is that if you want to accelerate the enterprise with AI, and more importantly, data-centric AI, because people still don't have labeled data sets in most of these enterprises, what are the right tools to use? What are the right processes to use? And how does the org even figure out what to do, how to get started? Like, and I'll tell you, the last mile is the biggest problem. And if you look at traditional enterprises like finance, retail, pharma, healthcare, and even the public sector, I mean, just take an example in, say, Switzerland, you have UBS. Think about how it needs to transform its banking completely and become the way we use newer distributed DeFi's, distributed financial institutions. So there's a lot of transformation that's happening in all these cases. Simple things like, we used to get handwritten notes from our doctors and pharmacy, and the pharmacy would actually read it by hand, and then they would give you a prescription. So how do you take a lot of this data that's already there and convert them into digital data? And it's not easy, because handwriting recognition has been an old problem. And then the other figure that I have over here is, in manufacturing, sometimes you have to put simple things like put this right screw in the right place in a manufacturing pipeline. And today, most manufacturing pipelines are getting more and more automated, whether it's through robotics or whether it's even just, if you buy on TV today, the most of the time, the quality control of the LCD panel was detected with computer vision. That would be my guess. But essentially, if you look beyond the traditional machine learning, in the machine learning community, we talk about large-scale problems in NLP, vision, speech, recommendation systems, and so on and so forth, right? But customers are struggling at a much more earlier stage, because customers are trying to use machine learning they're trying to figure out, how do you even map their business problems? So this is a survey that some folks did this year. Like, what are the customers trying to solve with AI? And the biggest problem is to map the customers, the enterprise business problems to machine learning. And if you can do that, that's like 80% of the work. And once you've done that, then the question is, where do you get data from? And this whole workshop is based on that theme. Like, how do you deal with data? How do you deal with, and these are some of the trends and challenges that the survey found, and I tweaked a little bit. So while in the research community, we are far ahead in figuring out how do you build better models, how do you do better MLOps from a research perspective, especially in academia, right? In the traditional enterprise, machine learning is just becoming a priority today, and there are more and more use cases, and there's a bimodal distribution. Like some enterprises, some companies actually have more than 25 models in production. Some companies have almost none. They're trying to figure out, and they're hiring their initial data scientists. So we have a huge distribution of what an enterprise looks like. And interestingly enough, more than technical abilities, sometimes success is about aligning multiple business and decision makers together to collaborate. So ultimately, human collaboration dictates the success of machine learning in a company. And it is true that some of the things that have been happening in the research and open source communities in the last 3 to 5 years have actually increased productivity, especially in MLOps, right? But if you look at the traditional enterprise, people are still struggling because data scientists are not the best people to do DevOps and system engineering. The biggest problem is integration. So if you look at a company, you have data scientists on one side, and then you have the enterprise IT on the other side. Like enterprise IT doesn't understand the nuances, all the nuances of that the data scientists are talking about and doing, and vice versa. And the data scientists don't actually probably know all the system level stuffs and the compliance. Like if you go to any bank, right, the amount of regulations and regulatory compliance stuff that they have to do is just incredible. So if you want to take your models and put them in production, you have to work with a whole set of challenges. And the next step is, so once you figure out that, okay, you're going to do it, now the question is, where is your valuable enterprise data that you're going to act on? And interestingly enough, when I was a grad student long ago, and I've seen this thing, like you wanted to do a machine learning algorithm design, you would assume that there is a good data set. Now, that assumption is still true today. I mean, if you look at most of the papers, they look at reference data sets. But in the real world, the data is in all kinds of places, and it's not even in the cloud. Most people think that they can go to Google Colab and start doing machine learning. But what I see, even in my team, so in my team, we look at a lot of time series data. We're beginning to look at log textual data also to solve different optimization problems. The hardest part that a data scientist comes into our team and faces is like just doing ETL. And the ETL can get really crazy. And typically people think that, okay, I'll take the data, I'll put it in the cloud, and then I'll do training, but it doesn't really work that way in real life. Why? Because your data might be in all kinds of devices. And some of these devices actually can generate ridiculously large amounts of data that you can't. The hardest part is to even ingest the data. I'll give you an example. If you take any genome sequencing or a biological imaging like electron microscope, an electron microscope can generate tens, if not hundreds of terabytes of data per day if it's operating at full capacity, 10 hours a day in a lab. And the oil rigs generates humongous amounts of data. So we spend a lot of time actually just managing the data rather than doing the machine learning. And I've not even talked about the reference data sets. So creating reference data sets takes enormous amounts of time. Even in my team, like that's been a huge challenge. And what we've realized is, and this is another thing. So 3 years ago, we figured that this would be a big problem, a bunch of us. And a bunch of us went and created this thing called Kubeflow for MLOps. Then Matthias created MLflow. But we did a lot of surveys internal within the open source communities, and we asked a lot of companies, where are your teams spending all your time? And that's the survey. It's a survey result that is still probably true. And what we found out is customers really wanted managed data-centric. Basically, customers wanted repeatable, reusable pipelines that are like Lego blocks, and they connect the data and the machine learning models more easily, so that the data scientists can actually do their data science, like build models. And then the models are in some artifactory, and then the production DevOps engineer can take those models and put them in production, do model monitoring, and then give the feedback loop, basically through GitOps or something that triggers more label data collection, more training, and then it's a loop, right? And typically, when you come to the point of workflows, there are many ways to do it. You can use many of the existing tooling like MLflow, Kubeflow, or you know what? You could take a workflow language like Airflow or Argo and just write it yourself if you have custom workflows. So it's solvable with engineering, and it's mostly being done in open source today. And this market has become so big in the traditional enterprise that it's going to be a multi-billion-dollar market in 3 to 5 years. So if you're looking to get into the industry, this is a great time to be in the machine learning engineering industry. Or whether you want to do a startup or in companies, this is a big thing. This can actually impact all verticals. However, because it's a new field, there's a lot of confusion. There's a lot of startups in the space. So if you are, so I'm going to use the wear my own enterprise hat, and if I were to choose stuff, like it becomes difficult for my team to figure out, what are the tool chains to use in each part of the life cycle. So these are some of my opinions. Like, I'm in my team, we bet on open source because we don't want vendor lock-in, because we don't know which startup will make it. And we use open source for our core infra, completely open source, so that we can rely on the communities, strong communities of smart people. And then we also use leverage companies that support that open source. So that's becoming a good model. And we are pretty much embraced Kubernetes for all infra. And then, the biggest problem is taking our machine learning workflows and integrating with the existing tools and processes. That's a very hard part. And again, this has been, and I think a lot of people will talk about this, that we really need to figure out how do we integrate traditional workflows with external partners who can do labeling for specific tasks, and also internal labeling teams. So now the data labeling part is becoming the things that have changed between 3 years from now. I mean, things that changed 3 years ago, but between now and 3 years ago is basically now we need to figure out how do we integrate labeling teams and partners. But otherwise, we were very focused on getting the model management workflows. Now we have to do data and model. And the other thing to remember that we've seen is, like, whatever engineering practices you do, it has to be across clouds. Most enterprises use more than 2 to 3 clouds for different things, and one of the cloud being on-premise. So having said that, I don't have much time, but I'm happy to chat later, and really happy to collaborate on some of this. Like, some of the directions that we see in data-centric AI, enterprise AI, I call it EAI, is this, right? If you look at current machine learning infrastructure, it's very disaggregated. If you think about, you want to train a large data set, and you want to do, whether it's GPT-3 or DLRM, you'll spend a lot of time. Your data is in a object store or files or something in a storage device, and you have compute clusters with pick your favorite accelerators and CPUs, and over a network, you're doing a lot of back and forth to do ETL and to just load, just assemble your TF records to even before. So think about what happens before you start your TensorFlow or PyTorch job. What is happening to the data? You're doing a lot of back and forth. Your GPUs are idle. In fact, there's a recent paper I saw from Facebook, I think, where they said that they spend a lot of time and power in the ETL versus the actual GPU based training. So current ML infra is disaggregated, but there's a new trend that I'm seeing, and we are also trying to figure out how to leverage that trend, is how do you do push down ML-friendly computational storage for any kind of distributed learning, whether it's split learning, federated learning, or just traditional multi-node learning. So I think that's going to be important. And if I would love to have conversations around how do we do this on standardized storage APIs. So if you, as a research scientist, you can go and really build custom storage infrastructure, but that will be very hard to productize. But if we can think about S3 compliant APIs, because S3 is everywhere, right? And then see how do you provide S3 has S3 select, for example. Using S3 select, how do you push down S3 select and UDFs and all that? How do you push down ML training pipelines? That would be really good. It'll change the game, basically. And then how do you do data-centric workflows where, so let's say you take MLflow or Kubeflow or whatever favorite workflow engine you have. How do you in real time collect data from edge devices like a camera and connect it to labeling algorithms that you yourself design or get a labeling partner to API? There are many startups who just give you API-based labeling services. And how do you do relabeling, data fusion? How do you kind of integrate that feedback into these workflows? There's a lot of engineering work to be done in workflows, but I think there's some research problems too on user feedback based model training with labels. And then there's a new area that I think we have started to look at, and it's data-centric reinforcement learning. So if you think about enterprises, and a lot of control systems have been there in enterprises for multiple decades. And for doing good control systems, you can use reinforcement learning. And so how do you use data-centric techniques to choose action spaces, trim action spaces, and speed up reinforcement learning? That's something that we are beginning to look at. And we have some early work in that space. So and I'm out of time, so would love to take questions, or I'm around, so I'm happy to chat online. And that's pretty much it. Thank you.
Thank you very much, Debo. Very nice talk, and a lot of opportunities and challenges to be done here, also from your viewpoint. Yeah, we're running a little bit out of time, so if there's any question, feel free to reach out to Debo. So his contact is on the workshop website, and he's for sure happy about your comments and everything. And thanks again for getting up so early and giving us your thoughts.
It's always a pleasure to talk to
Great. Thank you.
Folks in the academia and research communities. Thank you.
Thank you, Debo. All right, so moving up to our next session, I'll hand over the microphone and the moderation to Kenza, please.
Thank you, Cedric. So now let's take a break from the very technical part, and we'll be back to more technical talks at 4 p.m. But let's start our startup session. So I'm very pleased to welcome today 4 great startups, namely Lightly, Syntheticus, Lattice-Flow, and Modulus. They offer advanced solutions for data curation, cleaning, and evaluation. And I'm very happy to give the floor to Igor to present its startup Lightly.
Click this off. Thanks a lot. Hi, everyone. So today I have the pleasure to talk about Lightly, a spin-off from ETH Zurich. Before going into detail about Lightly itself, I will take a few minutes to talk about my story from ETH, graduating and becoming an entrepreneur. First of all, you need to understand a bit about my background. So I was always very passionate about building things, coding software. I spent a lot of time in my childhood actually doing web design or make my own games. Also played them with my friends and made some pocket money with it. And in the end, I got some real interest in robotics and eventually then at the university, also in machine learning. This passion for robotics and technology also brought me here to ETH, where I studied electrical engineering. And during my studies, I was a bit bored of all this theoretic stuff we did here at ETH. So I also wanted to spend some time on doing more practical stuff. So one of the things I did, I joined the student association AMIF, which was also a great time. I started with 2 other friends, a nonprofit, Unicorn Labs, to build prototypes for other startups. And I also spent a lot of time participating in hackathons, which are programming competitions where we basically build prototypes within a short time period. In my bachelor's, I also participated in a focus project where we built an exoskeleton for paraplegics. You see it on the right side, which also participated in the Cybathlon. During my passion for building prototypes and these hackathons, I also ended up winning the Hack Zurich, the largest one here in Europe, with a prototype for a machine learning model. So basically, within 42 hours, we built an application with an ML model in the background to detect deepfakes or fake media, essentially. And it was very tough because building prototypes with machine learning is very, very difficult. You need to collect the data, you need to train the model, and you need to deploy it, and all of that in a very short time period. Now, going a bit forward, today we're very happy that we made it actually into Y Combinator, one of the most prestigious startup accelerators in the whole world. And we are actually the very, very first ETH spin-off. Great that we made it. A bit unfortunate that we're the first one, but I hope there will many more follow. And it's very, very big actually for us as well, because we are focusing on machine learning, on data. Debo mentioned it before in the previous talk. We are actually in the middle of this whole industry now evolving. And it's actually great that we can also from Zurich out start a big company, also going to the US. If you don't know Y Combinator, they are the ones started as one of the first investors in these kind of companies. I guess most of you have used Airbnb, Stripe, or Dropbox, or some of the other companies here. Now, I talked a bit about myself. That might have been the more boring part. So let's talk about Lightly. What do we do with Lightly, and what kind of challenge do we try to solve? Especially when going from academia to industry, I myself doing all the prototypes, I was pretty baffled and shocked because suddenly it's not that easy anymore. We don't just train on ImageNet and we do some evaluation. We don't have perfect data sets where all the classes are well balanced and the data sets are curated. But actually I had to do a lot of manual work myself. I had to collect the data. I had to actually figure out what data should I actually use. Then I had to figure out how I can label it. And this labeling was also very tedious and time consuming. And as it turned out, I was not the only one. Lots of other ML engineers in the industry, lots of companies face similar problems. When we talk to companies now, they usually ask us, they don't even know what kind of data they actually have. We talk to car manufacturers working on autonomous driving, and they collect like 200 or 300 million video frames per month, and it's impossible to look at all of them at once. So all these companies create more and more data every year, and they kind of lack the overview of what data do they have, what should they use, what can they use to improve the model in the most efficient way. And in case you don't know this, typically we use supervised learning in industry, especially when working with images. This means we do classification, object detection, or segmentation. And this also means we need to label the data. You see it here on the bottom. This is from the Cityscapes dataset on the bottom right. It's basically even from Zurich. I think this is central, in case you don't know this, with the tram. So labeling one image can cost up to $10. And if you think about these hundreds of millions of images, it just doesn't work out. We cannot label all of them. And this is basically the kind of focus we have with Lightly. We try to help companies figure out what data they have and what they should use to label and then train their machine learning models. We use two technologies for that to be most efficient in that, because you can imagine it's a very scalable problem, which scales every year. It doubles basically because we have twice the data every year. And what we use is basically a combination of active learning and self-supervised learning. Now, this is pretty important because self-supervised learning is a new area. You might have heard about GPT from OpenAI or BERT from Google, which kind of brought self-supervised learning to the NLP domain. And since a bit more than a year, we also had some really big success in the computer vision area. And self-supervised learning allows us to understand unlabeled data or get some glimpse of what we can actually do with it and how we can work with it. And we use this with our open source framework to help companies understand, out of these hundreds of millions of images, what do they have? Do they have clusters? Do they have outliers? And then the second part is the active learning part, which also Debo mentioned really nice in the previous presentation. It's basically creating a feedback loop of a deployed model in production, trying to figure out how can we improve this model over time. Where is the model struggling? Where are the confidences low? Where do we have new data examples, or maybe even some sort of data drift or domain drift? And then we create this feedback loop. we use again our algorithms basically to figure out what data should you use in the next iteration, and then you label it again, train the model, and you continue with this feedback loop. As I mentioned, we use an open source framework which we built ourselves. So when we started looking into self-supervised learning, there was nothing out there, and we said like, hey, we need to really foster also the whole research community around that. So we built our own framework, and I guess the main author of the framework is also sitting here, Felix from our team. It's fully open source, even under MIT license, so you can even use it commercially. And it's super simple to use, has been built on top of PyTorch. And it also went a bit viral through some tweets from people like Jérôme Pesenti, the head of Facebook AI. And we use it internally all the time. So everything we built on Lightly is built on our own open source framework. And yes, it works. So what we do works. It was very hard in the beginning because when we started out like a bit more than 2 years ago, there was not this word data-centric AI, and everyone was still focusing on, hey, let's just build bigger models. Let's create new fancy architectures and train it longer. And for us, it was pretty difficult because we had to prove people that basically you can improve the overall accuracy by changing the data, not the model. And we basically also do benchmarks all the time. So we benchmark our algorithms even on academic and already curated data sets. But still there, we're able to show that, hey, if you compare Lightly with other methods like random subsampling, you can increase the accuracy of the trained model, basically. So what you see here on these plots is the training set size on the x-axis, like how much training data did we use, on the validation accuracy on the validation set. So basically you see that with less data, you can actually get better accuracy, which is pretty astonishing. But basically we see this all the time. One of the main reasons is that the training data we actually have has some sort of bias in it as well. So what we do is basically we regularize the data set. We have many nearby duplicates basically, which don't really help you during the training process. That was it. If you have any questions, feel free to reach out. We're also hiring. We have a new base now in San Francisco, thanks to Y Combinator. So happy to talk to everyone. Thank you very much.
Thank you, Gregor, for the talk. Now I'm very happy to invite on stage Aldo Lamberti to talk about Syntheticus.
Great. Good afternoon, Zurich, and good morning, Stanford. My name is Aldo Lamberti, and we at Syntheticus envision a world where data can be shared and analyzed easily, but without compromising the fundamental rights of privacy. And why is this important? Well, data is the world's most valuable resource, but actually its full potential is not unlocked. Take into consideration that out of the world's data, only 1% is really analyzed. So let me guide you through one of the concrete pilot projects that we're currently working on. All right, so we have Ben. He's the head of data at a Swiss hospital, and obviously he handles a lot of very sensitive data, patient data, our health data, and obviously he has also a lot of data about that, and he would love to get some insights about it, very needed insights in a fast and easy way. So he would like to share that sensitive data with Anna, who's a researcher maybe at the ETH or at the University of Zurich or wherever. However, there are a lot of barriers in there. There are IT silos, there are privacy regulations, there are compliance, legal and compliance, internal but also external, that actually hinder Ben to easily share that sensitive data with Anna. And in this specific case, just an easy contract set up between the hospital and the research institutes takes more than 6 months. And so when we're talking about patient data and health data, every second counts. So the solution for that is synthetic data. In that sense, we enable Ben to generate synthetic data out of his original very sensitive data so that he can easily share his synthetic data with Anna so that she gets the synthetic data, she runs her analysis on the synthetic data and sends back those valuable insights. And that can be very much faster than those contract setups. And in this case, we help Ben at the Swiss hospital really to save lives in a fast way. So the technology that we're using is a combination between generative AI, GANs, and differential privacy, which are within the field of the emerging privacy-enhancing technologies. And we developed a user-friendly solution so that Ben and Anna can leverage the unique power of those together. Yeah, so thank you very much, and very much look forward to hearing some questions from you or afterwards. Thanks.
Thank you, Aldo. So now let's introduce Pavel Bielik. We'll be talking about his startup Latticeflow.
Okay, so thanks a lot for the invitation. I'm very excited to be here. As said, my name is Pavel. I'm a co-founder and CTO of Latticeflow, where we try to empower companies to build and deploy AI models that are robust, safe, and reliable in production, which is becoming more and more critical for many companies for many reasons, as I will touch in the presentation. We are an ETH spin-off as other startups here as well. And we've been really working on this problem for last 5, 6, 7, 8 years on the research side. We are a group of leading researchers from ETH Zurich, including 2 professors in the field of AI and machine learning. And what we are trying to do with Latticeflow is really bring all this knowledge we have from the research and bring it into practice to help the companies. And one of the things we can do it, and we are very proud of, is, for example, we've been able to build essentially the world's first and best verifier that can both check and improve the robustness of existing models. And we even won a competition with leading other researchers in the world, including Stanford, MIT, DeepMind, and so on. And really the problems we are trying to solve is, on one hand, not only the robustness, but there are many other issues that all of you that kind of work with the AI and other models are kind of probably familiar with. And these models include, for example, things like blind spots and edge cases, where you might have seen examples from the news where, for example, Tesla car crashed. And of course, this is a very bad thing. And one of the main reasons is trying to understand why is this happening and what is the root cause. And in this particular case, this is a systematic failure of the system that fails when the model fails to recognize white tracks against the bright sky. And ideally, what you would like to do is recognize these failures before they happen in practice. Similar thing are failures due to spurious correlations, where the models that we are learning at the moment are so powerful that they're just exploiting all the small correlations in the data. And it just turned out, based on, for example, one recent article from Nature, that even most of the models that are trying to predict, for example, COVID from the X-rays are just turned out to essentially pick up these uncorrelated features and are not really doing the right thing if you really analyze them carefully, which is super critical because these are literally models that are used by the doctors in hospitals. And finally, also the problem of robustness, where essentially you train the model and you deploy it in the real world, but the real world is not the same as the one where you trained it. Like real world changes, the lighting changes, the camera angle changes a bit. And this is a problem of robustness and essentially stability of these models. And what we're building is a platform that enables you to go through this process and helps you to do this automatically without having to obtain a PhD in the field. So essentially the input is the training data in the model, and then we have a pipeline where you can auto-diagnose what are the issues, and then we can also suggest you fixes and help you improve it. And essentially this is really a continuous process that you would be employing throughout both the model building and the deployment. Now, essentially, because we are very closely affiliated with ETH and the labs, we are also mainly focused on also giving back to the community. So what I would like to do in the rest is just to give you 2 highlights of our recent work that we did from the research side, where the first one is a paper that will be presented next month at the New York's conference, which is about essentially automatically assessing what is the robustness of existing models. And this is essentially the first step. Like to figure out that there is a problem. And the problem we are addressing in this paper is that there is a lot of recent work that is essentially proposing different techniques how to improve the model robustness. But typically what happens is that once these papers are published, there is typically a researcher, maybe from Stanford, ETH, or MIT, who kind of sits down for 1 or 2 months and figure out like all the details in the paper, and then eventually figures out actually is not really what the paper claims because of this and this and this. And what we would really like to do is to essentially automate this process, which is exactly what we address in this paper, where we can now create a tool that instead of spending 1 or 2 months assessing how good the model really is, you can spend a couple of hours and essentially get much better intuition and also guarantees when you're deploying the system in the safety critical applications. Another application that we also worked on is a different work with one of the master students that was intern at Lattice-Flow, which is essentially problem of, there are these 2 words, like one word is you purely train for the accuracy, which is typically the business metric that people would have, which is like a 1 number that you have, or you can essentially train the model to be robust or safe. And these 2 things are not often, essentially, they don't often go too well. And you can see it by essentially taking the latest benchmarks, and you can see that there is typically like 10 to 15% gap in accuracy between these 2 models, which is often essentially large enough that companies are not willing to sacrifice this when they're deploying the models, because this is literally like connected to the business value that you have. So, and the problem that we looked at from the research point of view is how can we kind of get the best of both worlds? So ideally, you would have a model, in this case, something that has very high accuracy, but maybe low robustness, because this is just not how these models are trained at the moment. And on the other side, you have something that has very high robustness, but low accuracy, and kind of you want to combine it to get the best of both worlds. And again, this is kind of from the research side of what we can actually achieve. So these are the latest results that are now actually only published last month. And now, again, what we are doing at Lattice is bringing this technology to the companies that they can literally get both best of both of these worlds. So if anything, this is interesting to you, we are very happy to talk to you afterwards, or just contact us online. Thanks a lot.
Thank you very much, Pavel. And last but not least, let's welcome on stage Simone Severini. We will be talking about modulus.
Thank you very much for the great introduction. Good morning, good afternoon, everyone. Let's go to the main slide here. All right, so Modulus is also a spin-off from ETH. I recently joined as the VP of sales. So you will have a typical sales pitch I give to my potential customers. What is our mission? Our mission is very simple. It's crystal clear, right? So we know how hard it is to develop ML models, how hard it is to deploy them, and how hard it is to maintain them, right? So certain companies, as you can see here, they even struggle to deal with one machine learning model, right? When facing several customers in the field on a weekly basis, we understand that some of them, they've been trying to make models, or let's say that the life cycle to create a model is between 12 and 18 months, right? With an 87% failure rate. This is quite incredible, right? So you think about, as a data science, that not all the companies can actually afford data scientists first, and not all of them, they can actually attract them, right? So data science tends to go to the big companies where they get big bucks, right? So how do we actually democratize AI? So that's exactly our mission. We need to make AI so simple for any company to introduce into their basically business operation environment that you don't need basically expert resources, right? So we do have already quite a few customers. Some of them, they've been extremely happy, and most of them overall, they're really happy about the amount of time they saved in order to create those machine learning models. Just to give an example from one customer, data science took 3 months to basically create a model, configure it, tune the parameters, and put it in production. We, in 2 hours with our platform, we achieved basically the same performance. Now that's a big saving, right? So this is the view of our platform. So first of all, is an end-to-end concept, is data-centric. What does it mean? It means that we're going to start from the pre-processing of the data. Be aware, we are not doing data cleaning, right? So we're going to rely on third-party companies. The company should actually be applying the domain expertise in order to provide the perfect data set, right? So all what we do, we're going to basically decide whether is that useful for the creation of machine learning model. And then we come with recommendation. Remember this word recommendation. This is a system that is supposed to be used by non-data scientists, right? So it's going to provide you a step-by-step guide, and at each and every step is going to give you recommendation. Hey, look, this data need to be cleaned. Hey, look, this data need to be done, blah, 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 right? So we need to exactly do this. The second point, which today is available as a product, is the AutoML. AutoML is going to basically create a stream of machine learning solutions. Are those solutions ready to be deployed? No, they're not, right? We saw in the news what happens if you really get it wrong. So we need to ensure that there are mechanisms in order to ensure quality of the model. The model is performing good enough in order to be able to reach basically the production. And at the same time, out of those models, right, we need to pick the best ones. And the best one because they are tested against production data. At the end, we need to monitor. We need to understand if from an IT perspective, those models are working well, if there is a data drift, if there is a label drift. Those are the things we need to do, right? Now, this is not all. This would be a one way. Really, the novelty here is to basically have this feedback loop that at each and every time of the chain here, you should be able to actually recommend whether you need to do something on your data, right? So let's see a little bit more into the details, right? In the auto data feasibility, I say, okay, I want to have a machine learning model with this level of accuracy. That's where we set it there. And automatically the system is going to tell you, okay, you need some cleaning. Oh, yes, you need to go and do some sort of a data acquisition in the marketplace. The output is going to be a data set ready for AutoML. We enter into the AutoML, and then we're going to basically apply all potential models available in literature, right? Today, we started with the time series. We started the image classification, tabular classification, and tabular regression. I envision this over time to grow and encompass NLP, transfer learning, and so forth. So the output of this is going to be an ML solution ready for flexible deployment. Once that is done, we enter into the probabilistic continuous integration. Here we can say, I want to have a model which has the probability of 99.9% to be 1% better than the previous one, right? So we put a sort of a step in here. And how do we do that? We basically continuously test against the test data, right? Not only we are able to tell you if the test data, what is the optimal size of the test data? We heard before, to label certain data cost even up to $10, right? So we cannot really shoot to have the largest test data possible available. Why are we doing this? Mainly for one reason. We want to prevent overfitting, right? So using over and over the same data set is going to actually create problems in the long term. Then the model picker. So now we have a stream of solution, and then every now and then we test it again, the production data in order to select what is safe to deploy, right? Last but not least, as we discussed before, we enter into the monitoring, and this is where basically we check from IT perspective the resources usage of the model. We check the response time, we check the RAM usage, and so forth. But most importantly, we go and check whether there is a divergence between production data versus training data. So that's called feature drift, and then label drift, which is basically attached to the ground truth. So this process here could take weeks, months, depending on the data availability. To summarize, so what the Modulus has done here is a fully system-guided model, right? We want to simplify as much as possible. Today, we take the data set with a drag and drop, and what you get as an output is a Dockerized, right, model with REST API integrated, right? It's ready to be deployed and is language agnostic. We have the first probabilistic CI. So this is like a data-centric MLOps. It's not the traditional MLOps that you see out there. Is a closed loop feedback. We discuss about this. So we want to minimize the cost of data acquisition. And last but not least, we only want to deploy models which are good for deployment. Right. Thank you very much.
Thank you, Simone. So that's the end of the startup session. I invite our online audience to take a break, grab a cup of coffee, relax, and come back at 4 p.m. for the next technical part. And I invite our local audience to go join the networking session where you can ask all your questions to the startups and also grab a cup of coffee. Thank you very much.
Okay, so hello everyone. Welcome back from the little break. And my name is Bojan, and I will be chairing this session we have here, which we entitled Data Systems for AI Governance, which is a general topic. Let me introduce the first speaker. His name is Sebastian Schelter. He is an assistant professor at the University of Amsterdam. He does research in the intersection of data management and machine learning. And in the past, he's been affiliated with the Center for Data Science at NYU and Amazon Research. And his work, he's done work in the area of automated data quality validation, ML pipeline instrumentation, as well as giving ML models the ability to forget things. And without further ado, Stefan, do we have a connection? Or Sebastian? Sebastian is speaking, right?
Yes, can you hear me?
Yes, we can hear you. Hi, Stefan. Thanks for joining us. So the floor is yours.
Thanks for having me. I'm Sebastian. Bojan already introduced me, and my PhD student, Stefan Grafberger, is also going to co-present some of the work. So today we're going to talk about data provenance and its connection to AI governance. Before we talk about the specific details, I would like to spend a little bit of time to talk about the difference between machine learning in the lab and machine learning in the real world. And luckily, we've already heard a lot about this difference today, so I'll keep it short. So Felix, for example, talked a lot about that, and also a lot of these startups. So when we do machine learning in a lab, maybe as researchers or in some course in university, then the world is pretty simple. We have some static training data that's often already in a very nice form. And then we design some models on this data and evaluate on some held out data set how well they work. And the tools with which we work are pandas and Jupyter notebooks and maybe some machine learning library like PyTorch. And usually we can work on our notebooks. The data fits into memory. We can look at it. So a lot of things seem to be very easy in this setting. But once we move to the real world, as we've already heard today, things get way more complex. So we don't have a small fixed training set. What we have is several data sources, usually heterogeneous. This can be data lakes, log files, scrolls, APIs. And we have to consume data from these data sources, and they will also continuously produce data. And then we have to run some kind of data preparation stage to basically turn these often relational or semi-structured inputs into some vectorized training data on which we train our model. And then we deploy our model, and we have a second version of the pipeline, the serving pipeline, that takes new unlabeled data, again, converts it to some vector format, and then uses the model to derive predictions from that. And as part of this pipelines, we use all kinds of data sources. We use data flow systems, machine learning systems. So there's a big, rapidly changing ecosystem for running these, for training models and for deploying them and monitoring them. Now, the governance question that we have to face in these machine learning applications has lots of aspects, and there's lots of regulation that's already existing now in different parts of the world. And we can also expect to have much more regulation in the coming years. And here I'm going to walk you through some examples. So the most well-known regulation is the General Data Protection Regulation, GDPR, in Europe. And this regulation gives European citizens a set of rights, and I have some excerpts here. So for example, we as Europeans have the so-called right to rectification of personal data. So machine learning applications that use our personal data have to correct this data if we think there is an error in this data and we request this rectification. Then there's maybe the most well-known right, the so-called right to erasure of personal data, often also called the right to be forgotten. That means we have the right to request the deletion of our data. And the law says without undue delay, so this deletion also has to be fast. And furthermore, data processors have the obligation to keep records of their processing activities. And then there's also other kinds of regulation that is not directly related to privacy, but more to the prevention of discrimination. So for example, in the US, there are several labor laws or several laws that prohibit so-called disparate impact in decision-making in areas such as housing or employment, for a group of people defined by a certain protected characteristic, for example, race or religion. So basically, the machine learning applications that we build cannot discriminate people based on these characteristics. And also in other parts of the world, we are slowly seeing regulations coming up. So recently in China, there were some proposals to require algorithmic recommendation service providers to give users the ability to choose, revise, or delete user tags used for algorithmic recommendation services. So to basically give people back some form of control over the data that is stored about them and the recommendations that they see. And all of these regulations are written usually on a very high level without a definitive technical specification, which I think is good because the technical details are very hard and they change a lot. But I think it's our task as researchers to think about the how to implement these regulations in the current systems that we have. And on the first hand, this might look like an academic exercise, but before we go into technical details, I would actually like to mention two examples that showcase that these data governance problems are very real and are very, very serious. So on the left, you see an article about recent developments in Afghanistan. As you've probably seen in the news, the Western forces retracted from Afghanistan and the Taliban took over the country again. And there's a lot of fear of, and also a lot of cases of retaliation against Afghan citizens who worked with the Western forces. And basically a lot of them had to go into hiding and have to make sure that the new government cannot figure out that they actually work together with the Western forces. And one of the traces that about this activity is actually digital traces. So I think even the US Defense Ministry, they deleted some data from their websites. And it's actually a case where this right to have your data deleted, this right to be forgotten, cases people need to have the ability to remove all these digital traces. And there's another pretty horrifying case that recently became public in the Netherlands. That's this blog post that you see on the right side. And that's a blog post from a couple who expected a child and unfortunately lost this child at the end of the pregnancy through a stillbirth. And they have been searching for baby products and all kinds of online services and websites during the time of the pregnancy, obviously. And the horrifying experience that they had was that after they lost their child, they could not escape these recommendations. These websites had learned user profiles about them, and these websites still thought that they would be interested in baby products. So they basically, whenever they visited an e-commerce website and saw baby products, they would be re-traumatized through this. So again, I think this is a very crucial example that shows that people need to have the right to control this data, to delete their data, and also to have this right enforced in a timely manner. And from a technical perspective, the problem is that enforcing these regulations in machine learning pipelines is actually very, very difficult, and there are some unsolved problems. So if we go back to this high-level machine learning pipeline and we look at the case of, let's say I want to have my personal data erased, then there's a couple of places where this data is stored and where it needs to be deleted. So obviously it's stored in the primary data sources. Hopefully the organization running the pipeline should know this and should be able to directly delete this. But we also created training data from these records. And in many cases, this training data is only an encoding of the data. So it would be relatively easy in many cases to restore the original data from this training data. So we should also delete these intermediates. And even more complicated is the fact that some models might also learn some embedding or some kind of compressed representation of the data. So in order to be really sure, we also need to update or retrain the model so that the model also forgets this data. And especially this retraining is very, very difficult to do in an efficient way. The other case that I would like to talk about is with respect to this prevention of discrimination. And as I mentioned, there is this notion of so-called disparate impact. And here's an example of challenges that we have when we want to compute the disparate impact ratio over some prediction pipeline. So let's say we're interested in this disparate impact with respect to people over 70. Then we need to compute this disparate impact ratio. And basically we need to know how often does our classifier give the positive, or machine learning model, the positive outcome? Maybe, I don't know, you grant a loan to somebody or something like this. How often does this model give this positive outcome to people from the protected group? In our case, people older than 70. And we need to compare this to the number of times that the model gives this positive outcome to basically the rest of the population. And then there are some constraints on the ratio defined in the law. Now, the problem is that in order to actually compute this, we need to keep track of this sensitive attribute through the pipeline. And it might be the case that we have this age attribute in the original data, but in many cases, it might be illegal for the model to use this attribute because it's a sensitive attribute. So actually our data preparation pipeline should filter out this from the data and not have it as part of the training data. But then we create this unlabeled serving data. Our model makes predictions for this data. And then in order to compute this ratio, we suddenly need to know this age attribute again, because we need to figure out for all the positive predictions to which group they belong. So again, this is something that would maybe be simple in a Jupyter notebook in a lab, but in complex deployed pipelines, this is actually a very, very difficult problem. And if we look into practice, and if you look into surveys from companies, then you see that there is basically some kind of Wild West landscape out there at the moment. So we have these pipelines, they consume data from many different sources. And these pipelines are also built from different libraries and engines that from an ecosystem that rapidly changes. They might use different abstractions for processing the data, different data representations. So it's really, really difficult to systematically figure out what's happening to the data. And in some sense, this is because there is no real consensus on how to model machine learning pipelines and reason about them. It's not like in the database world where we had the theory first and then we built the systems. Here, in many cases, it's the other way around. We first built the systems and now we need to figure out how to think about them. And so the support for this data governance in many of these platforms is at best unclear, especially with respect to data deletion. And I think even companies who want to implement these regulations have at the moment to build very customized, tedious in-house solutions for specific cases. And what we argue in our recent research is that there is a particular meta information about pipelines that we need in order to solve all these problems. What we need to understand in these cases is the so-called provenance of the input data. So we need to figure out which input records contribute to which rows or which vectors of our feature data. So if we look at the picture, we have, for example, one point in our training data, and we have a pipeline, and maybe this point in the training data is computed from these three different inputs from the different input sources. And if we can figure out this relation, if we can automatically extract this, then we can also automatically solve some of these regulatory problems. So for example, if we have this provenance, then we know which records we need to delete transitively. If we delete these records, because they belong to some person, we also need to delete this data point, which probably is an encoding of the data. If we know this provenance information, then we can join this data point back with this data and then, for example, figure out sensitive information like this age information to compute this disparate impact ratio. But in order to do that across a large set of machine learning pipelines, we first need to have a way to reason about our machine learning pipelines. And in the last years, there's been a lot of work on basically doing lots of things automatically with these pipelines. Bojan already talked about this earlier today. And we think that there's slowly a certain common view on these pipelines emerging, which allows us to automate a lot of analysis of them. So typically what people do is they model this data preparation stage of a machine learning pipeline, for example, for classification as a data flow computation from relational inputs or heterogeneous data sources that are often in a star schema. And then the output of this data flow computation are matrix outputs. In a classification use case, for example, this would be the feature and label matrices for the training and the serving data. And the actual operations which these data preparation pipelines apply are often very similar, so very, very simple. So there's basic relational operations like selections, projections, joins, and then often this is followed by some encoding and linear algebra operations that turn the relational data into matrices like one-hot encoding or scaling. And in many cases, we can view them as extended projections applied to the data. Now, the nice thing is if we take this view, then we can reuse a lot of existing research from the data management community on how to compute certain notions of provenance. So a very simple form of provenance is, for example, the so-called Y provenance. And the idea here is that we assume that each of our inputs is tagged with some identifier. So for example, the identifier could be the sequence number of the data source and the number of the rows. So this is the second row in the first data source. This is the first row in the third data source, and so on. And what we actually want is, we want to have the set of identifiers of the input records as an annotation to all the outputs of our pipeline. In this case, the feature vectors. Because if we have this relation, then we can find the input data points and we can automate many of these regulatory use cases. And the nice thing is that this is well understood for relational operations. And what you basically have to do is you have to propagate and combine these annotations while you run the pipeline and while the data moves through the pipeline. And there's a lot of theory on how to do this. And we've already done a couple of work on this in the last years. And I'm going to hand over now to my student Stefan, who's going to talk to you a little bit about how we actually implement this.
Hi. We recently proposed a Python library that can do this sort of provenance computation for machine learning pipelines, as long as they use libraries like pandas, scikit-learn, and keras. Our library, ML-inspect, can automatically instrument these native machine learning pipelines in Python. It works for unmodified Python code and does not require any changes to the code, as long as it's written using certain declarative abstractions. The input is really only the file path to existing Python or Jupyter notebook files. Sebastian talked about these declarative abstractions previously. Libraries like pandas use mostly relational algebra operations, and feature encoding libraries like scikit-learn can be treated as extended projections. ML-inspect instruments the unmodified user code automatically, so we know when certain functions from these libraries are called, can override and patch the behavior of these functions. Then, during the execution of the user script, we can build an abstract representation of the pipeline, a query plan. We can look at the data that flows through this directed acyclic graph and do additional computations without changing the behavior of the user program. We use this to generate and forward propagate annotations for the data, like the Y provenance Sebastian discussed earlier, and compute and materialize information that we need for further analysis. In the end, the stack and materialized information like the Y provenance for certain operators can be used to apply different analysis techniques and automatically detect different issues. For example, we can try to detect certain cases of technical bias in data preprocessing. There are many interesting performance aspects to consider when implementing something like this. If you're interested in that, I can recommend taking a look at the paper. Overall, we see ML-inspect as a runtime for a variety of different use cases and tried not to make too many assumptions about the way it's used. Once we finished an initial version of ML-inspect, we started looking into different use cases and started working on a CI tool using ML-inspect. The CI tool is called ArgusEyes. It's important to note that ArgusEyes is currently still an early prototype and heavily work in progress. When instrumenting machine learning pipelines, we need to decide which data we want to keep around for potential retroactive analysis. If we would just store everything on disk, we would have to keep way too much data around. A naive approach would be to just store all intermediate data for all operators in the query plan. But for a machine learning pipeline with a query plan with 50 nodes, you would have to store 50 copies of the data. And this would get way too much data very fast. However, having the ability to compare different past runs of a machine learning pipeline is crucial, and we need to allow retroactive comparison and analysis. In Argus eyes, the core idea is that just storing the initial relational inputs, the matrix outputs, and the corresponding data provenance is both manageable from a data size perspective, while also being sufficient for a lot of use cases. In Argus eyes, we store this information for every run automatically using MLflow. Then we can analyze it retroactively. We also use heuristics to detect what kind of machine learning pipeline we currently deal with. For example, to detect that something is a classification pipeline. And we can then use this information for both immediate issue detection and also future retroactive analysis. Some examples: we can configure Argus eyes to automatically compute fairness metrics like disparate impact. We can screen for different correctness issues like an overlap of train and test set, can detect label shift and covariate shift, and we can also do data debugging. For example, we can compute Shapley values automatically for these machine learning pipelines. And thanks to MLinspect, we can do this automatically for unmodified Python code. And there's no need to introduce logging statements like you need to do when using tools like MLflow directly. Overall, using Argus eyes as part of your CI pipeline is really easy. For example, we build a GitHub action where you only need to provide a small config file, information like the path to your Python pipeline code. Then we can automatically compute and log all information with each commit and fail the CI pipeline when you find any issues. Then finally, if you want to learn more about our research, you can visit the website ssc.io. And lastly, it's important to reiterate the limitations of our approach. It only works if the pipelines are written declaratively and if we can understand the semantics of the code because of that. So that's it, and thanks for your attention, and we're happy to answer your questions.
Cool. So thanks for your talk. It was very interesting. I happen to be partially, also sharing a lot of the sentiments that you guys express, especially for the strives towards, doing more due diligence for over, when you do data management, like you tracking provenance and stuff like that. If there are no questions, I want to shoot a question then towards you. So I guess my question is around the whole adoption issue of things like this, like tracking provenance. So it's my impression that there is some resistance of people using these new things because day-to-day people have been used to doing things their own way. So have you guys experienced any resistance? And in general, like what is the feedback you're getting on the tools that you're building? So do you think that we can have an approach to move this these ML pipelines into something that becomes more manageable in the future?
Thank you. I think that's a very good question. And before I became an assistant professor, I spent a couple of years in industry, and I actually experienced some of the problems that you talked about myself. So I've developed a similar system to MLinspect, so system that can record the metadata from machine learning pipelines, with the big difference that in this system, we did not automatically instrument the code, but we asked people to insert logging statements in their code to record all the information that that is required to then do this retroactive analysis. And unfortunately, it turned out that data scientists in their day-to-day work don't have the time or the willingness to put these logging statements into their code. So it was very, very difficult to get an actual adoption for the system. And that's for us the reason why we work with automatic instrumentation. So I think for me, that's the road forward. So what we try to work with the libraries that are already out there. We try to work with pipelines that consist of pandas code, scikit-learn code, and then maybe a Keras model in the end. But as we said in the end, our approach is limited in the sense that we need to have code that is written in a relatively nice way. But in general, I think there is a move to more declarative systems in all kinds of research related to machine learning. And I think this is basically the chance that we have, because once we define things more declaratively, then we can enable a lot of these optimizations and automatic recordings of metadata.
Okay, cool. Thanks, Sebastian, once more for the extensive answer and for a very nice presentation.
Thank you.
And with that, I would like to invite our next speaker. His name is Mislav Balunovic. Is he with us?
Hi, can you see the slides?
Yes, hi Mislav. So Mislav is a third-year PhD student at ETH Zurich. He's working with Professor Martin Bechev, who is also going to do a talk after him. And his broad interests include trustworthy ML, and he particularly focuses on problems of robustness, fairness, and privacy. And without further ado, Mislav, the floor is yours.
Hi, everyone. So today I will tell you about our recent work that we did on creating provably fair AI systems with the focus on learning fair representations from data. So now we have seen that decisions of ML models impact a lot of people in real world. So ML is used to predict whether some person will get a loan, whether to predict whether a person will commit a crime, or to decide whether some person should get hired. And what we have also seen are many news articles saying that these models are unfair and biased. And moreover, some companies are even stopping to use ML for solving these tasks now. At the same time, regulatory agencies such as European Commission are creating regulations with the goal to ensure that AI systems do not create or reproduce bias. So to actually ensure wider adoption of fairness in machine learning, we need to address the following key challenges. So we need to know how to define fairness. After we define fairness, we need to know how to train and enforce fairness into our ML models. And finally, after the model is trained, we actually need to prove that this model is actually fair. So let me tell you some details how to tackle these challenges. So in terms of definition, one approach that community is considering is individual fairness, where we say that two individuals are similar if according to some defined metric. And then individual fairness means that if they are similar, then a prediction of ML model should be similar for these two individuals. The challenge here is how do we actually define similarity? And then group fairness is a bit different. It says that if I split my data into two groups based on some sensitive attributes such as race or gender, then we should require that prediction of ML model averaged across all the individuals in the group is same for both of these groups. And here the key challenge is kind of how do we actually define these groups? So for enforcing fairness, there are actually three different families of approaches. And in this talk, I will focus on data-centric approach that we call representation learning. So here the idea is that we have some input data, and we're going to train a new representation of this data that will be debiased. So what does this mean? So this means that if I train any ML model on this debiased data, then by construction, this model will be fair, no matter what ML algorithm is used to train this. So some setting where this is very useful is you can imagine that there is a company that has some input data on its users, and there are many different teams that are building different products, and each of them is using ML to solve a different task. So then each of them wants to enforce some notion of fairness, but this is difficult because they might have different idea what fairness means, or they might not have expertise in their team to actually build a fair ML model. Now this pushes, this representation learning approach pushes the entire fairness concerns into representation learning. So once we trained fair representations, then any ML model that's trained on this debiased data will be fair. And moreover, it will be provably fair, as we will show later. So the two other approaches are called in-processing and post-processing, but I will not touch on these in this talk. They will be useful in some other context. So here we are focused also on three different application domains. So tabular data might be useful for tasks like long prediction. Images are also widely used, for example, face recognition and also NLP. But techniques that I will present are very general and they can be applied basically to any application domain. So our first approach to actually enforce individual fairness is based on the following. So given some two individuals, X and X prime, that are similar to some similarity fairness notion phi, we want to ensure that their latent encodings Z, so their representations, that they are close by in this latent space according to some metric, let's say L2. So how do we train this? We constantly search for counterexamples. We search for X and X prime that are similar, but their latent representations are far apart. And then we try to minimize this distance. So this is usually called adversarial training. And then once we have this, we can train some classifier that is robust to perturbations in the latent space. And then it's easy to see that the composed model will be robust to these changes according to some similarity notion phi. So something I haven't mentioned is how do we actually prove that model is fair. So in next talk, Martin will tell us more about techniques that are behind proving such properties. And then another domain we're interested in, as I mentioned, is images. And here, what is very difficult is to actually capture the similarity notion, because if I want to define images that are similar to some individual, this might be some very complicated curve in the image space. But then we can use generative model to actually capture this set of similar individuals, because in the latent space of generative model, this might be some simpler shape. And here we actually want to use techniques based on randomized smoothing, because in image domain, these models are much more complex. And something to note here that now our guarantees will be probabilistic. So two similar individuals will be mapped with high probability to some similar points in the latent space. And now switching to group fairness definition. So here we have two groups defined based on some sensitive attribute such as race or gender. And here these two groups have different probability distributions, P0 and P1. Now imagine that we are training some classifier that takes input X and predicts some label. Now this classifier would be able to reconstruct a sensitive attribute from X and use this for its prediction task. And this is exactly discrimination, because it can recover sensitive attribute and then use it to predict. Then it can discriminate against one of these groups. So how do we actually solve this problem? We actually, again, learn a new representation of this data. So we map X to some Z in the latent space, which has a property that for some Z, probability that it comes from both groups is roughly the same. Then no classifier can actually recover sensitive attribute and use it to discriminate. And the key idea behind our approach is to use encoder normalizing flow, which enables us to compute these densities in the latent space, which is something that normal architectures cannot do. And then we can obtain provable guarantees on maximum possible unfairness of this classifier that is using this data. So to conclude, I talked about fair representation learning approach. I told you about two techniques for individual fairness and one technique for group fairness. And the key takeaway is that we can transform our data to a new debiased representation such that we can prove that any classifier that is built on this data is fair. With this, I would like to conclude my talk, and I'm here for questions. Thanks for the attention.
Cool. Thanks, Mislav. Yeah, applause, why not? So Yeah, this the chat is not so lively, unfortunately. So, so let me try to shoot a question, and that is it's probably going to be a very basic question or a too general question. I'm not really sure because I guess I'm kind of like not an expert in the area, let's say. But when you were mentioning those sensitive attributes, a thing that came to my mind is like, how do I know what is a sensitive attribute? And I guess the question is there a way for, I'm thinking of it as in terms of like a user wanting to define what sensitive attributes are in order for your system to work. However, I don't know exactly what sensitive attributes are. Maybe I know some higher level thing. I have a higher level idea of fairness, but I don't have a specific attribute to specify for you. So is there a way to bridge that gap? Or has anyone looked at it before?
Yes, so this is actually like one of the active areas. Like basically here we are assuming that you know sensitive attributes. So this would be something that's written in regulations, like you cannot discriminate based on race or something like this. But then, as you're saying, there is more difficult problem where you actually don't know this, and you're kind of trying to learn what is sensitive attribute from data. But currently, this is very hard.
Okay, cool. Well, I guess in the interest of time, I want to thank the speaker once more, and I would like to invite the next speaker. And the next speaker is Professor Martin Becher.
Oops. Hi, guys.
Hello. Hi, Martin.
Hey, how are you?
Good. So Martin is an associate professor of computer science at ETH Zurich. His research interest is in the intersection between ML, probabilistic reasoning, and programming languages. He got this PhD at Cambridge University, received many awards, including the ACM SIGPlan Robin Miller Young Researcher Award. And also, he's very active on the startup scene. He co-founded 3 startups, 2 were acquired in 2020, and the latest one is Latticeflow being showcased here. And without further ado, Martin, I want to let you have the floor.
Okay, thanks a lot. Thanks, guys, for inviting me. Great event. Can you hear me first of all? Everything is good? Yeah. Okay. Cool.
Yeah, we hear you perfectly.
I can see some of you. Okay, so I'll try to keep the last talk a little bit more high level to give you a bit of an idea what we are trying to do here, and try to stick to the theme of the workshop on the policy and data and so on. So essentially, what I want to talk about is of this idea of trying to build machine learning models beyond thinking beyond standard accuracy. So thinking about providing certification guarantees of very important properties of models. For instance, what Mislav talked about, like individual fairness, group fairness, robustness to data shifts, and many other, basically any other safety property that you may actually care about to build your model to satisfy. And this somehow, one of the underlying points here is that this seems to require actually not just dealing with finite data or bounded data where you have a data set and you train the model to get good accuracy, but also deal with essentially infinite data. So I want to illustrate this point in the talk and kind of argue that in order to do that, to do any kind of certification, and you need to deal with infinite data, and to deal with infinite data, you need to potentially rethink many of the more fundamental parts of the machine learning pipeline. So to do that, I'm going to illustrate this on the problem of robustness to data shifts, but exactly the same reasoning is applied to basically any other safety property. So let's just let's get to it. So if you look at this robustness to data shift problem, the data shift could be adversarial, could be just a natural shift like a weather change, and it typically happens. There are various scenarios where it can happen, but one scenario is where you train your model on some data on some training data that you've gathered. Maybe it's synthetically generated and then augmented with generative model, or however you obtain the data, and then you are actually deploying this model in production or even at test time, and you're actually getting slightly different distribution than the one that you're getting samples from a slightly different distribution than the one you trained on. And then this kind of issues can happen, like somebody puts a sticker on a stop sign and then the autonomous car kind of gets confused what to do and takes the wrong direction. It can happen in the medical space where if you train on certain data and then another data comes from another device, like an MRI device or some scanner, which is slightly different, but to the human eye may actually look the same, but not to the machine learning model, you actually get very poor behavior. And this has caused some people to think that the way that you actually build models, if you want to go beyond accuracy, is into any form of guarantees, it's somehow fundamentally flawed. So let's just look at a couple of examples why the problem is actually hard and why it kind of you need to think about infinite data. So if you stick to this robustness to data shifts problem, again, be it adversarial or non-adversarial, it doesn't really matter. The non-adversarial setting, I think, is actually much more important from a production perspective. So if you take something like this, when you want to build a model which is robust to perturbations of an image, various combinations of rotations, flipping, brightening, noise, and so on and so forth, and then combining those transformations on the image, you can have basically arbitrary program with conditionals where the transformations are just functions. You can make them probabilistic too. You would essentially end up with a very hard problem to where you try to prove that your input, even this, like your input is your network or your model is robust to perturbations, which are compositions of any of these functions here with arbitrary parameters like rotations between 0 and 30 degrees. This is already essentially generating infinite data because of interpolation and other operations which are used. So you cannot just enumerate. This is why the problem is hard. You can just take a point and kind of enumerate and explore all the perturbations that a data shift specification will kind of capture. So this already gets tricky, even in cases like this, and even with state-of-the-art research, we are still struggling to establish any kind of properties on this kind of problems. Just so you don't get the idea, it's hard-coded properties. You can actually the same problem arises with generative models, to where you can take two pictures that you see here on your left, like A and B. You can put them from an encoder and then specify a specification, kind of like anything on the line spec between 2 points in the latent space should classify the same. So this may involve generative models, may involve programmatic models that go downstream to some classifier. How you actually obtain this kind of infinite data in this particular case would be all the points that sit on the line between two points in the latent space. There's not just the image domain, there is also the audio processing domain, to where you have some recording, you change the volume of the recording, you want the classification of the word that you're saying stop or go to be correct. And so you need to deal with, if you want to guarantees of any kind, you need to be able to kind of say something about this infinite possible, continuous space, infinite possible perturbations that can happen, even when you're talking about like a single input, let alone when you're talking about arbitrary safety pre-post conditions, which happen if you are considering, for instance, machine learning models employed in air traffic collision avoidance, or as part of some robotics tasks where there is another component which is doing differential equations. So the inputs oftentimes are kind of spanning the infinite domain. And so how do you actually deal with this, right? So there are two parts here. One has to do with the, you're given a model, you want to certify that that's what it's supposed to do. And this is one way to deal with this infinite data problem. Just to show it on an example here, is that you have let me just take a annotation here. Is you have something like this, even if in the very simple case where you just have an image over here in red, and you put some region around it, like every pixel you can perturb it within some interval. So you basically get some kind of hyperrectangle in whatever dimensions the image is. You would get a very large set of potentially infinite set of images here. So you cannot just enumerate this, even 784 pixels, 2 to the 784 is basically unfeasible. And so you need to have a way in which you can actually take this infinite data captured by this shape here, which could be captured in some symbolic shape, some symbolic constraints. And then you need to change fundamentally the way that the functions of the neural network work, like the affine transforms and the different activations like sigmoids, tanh, revius, and whatnot, in order to work not only on concrete points, but now on these symbolic points that capture infinite data. And so that's what a lot of the research in the last few years has dealt with, efficient ways to propagate this kind of infinite sets which are described in some bounded way via, let's say, some symbolic formula. And so what it essentially you need to do is you need to change, you need to lift your, these arrows here, which represent the activations or the functions of the neural network, to their symbolic counterparts in order to now propagate these symbolic shapes and get other symbolic shapes. And when you get to the end, you'd get some big symbolic shape, which is captured by some constraints, and then you can prove the property you care about. So that's one step you need to do. And there's, as I mentioned, tons of work on this, very active area of research. How do you make this propagation here so that it is not too imprecise, doesn't lose too much information, but it's also efficient, because otherwise you're not going to be able to handle big networks. So very interesting area, how to deal with infinite data. But now if I take just a network or some model which is not trained to satisfy the property of interest, be it fairness, robustness, or whatever safety property you care about, you're not going to be able to prove much with this method or with some other method. And so what you need to do is you need to come up with ways in which you are training your models so that they satisfy the property of interest. And what this means is that you need to be propagating like no longer kind of batches or like points for the network, but you need to be propagating the symbolic infinite data sets. Okay, so you take these shapes, and just like before, you push them through, you'd have these clever, abstract symbolic transformers that push things through. And then once you do that, you're going to end up in some shape. And notice that you don't talk about verification here at all. And then what you want to do is you just want to, take the shape that you get here at the end, which potentially captures anything that could happen to any point here in the beginning, and potentially more, but it is still sound. And then what you want to do is you want to change the basic machine learning problem. And so you tend to pose this kind of min-max optimization problems, where if you actually, for a second kind of remove the max here, and for a second remove these funny shapes here. Okay, let's just like remove this thing over here, essentially, and let's just make this an X here. Okay, then you would end up with a standard machine learning problem. So there's actually no difference whatsoever. So the thing that is added is these things, red things that we scratch here. And what it really does is something very simple. What it says is, let's change the problem to be such that we can change the weights of the model such that when this abstract or whatever symbolic activations are firing through, we are trying to get smaller and smaller shapes here, so we don't induce too much over approximation. So that's how we are trying to train our model. We're trying to bias it towards this. And so what this means is that you need to differentiate through this, no longer the activation functions, but the abstract versions of these activation functions, which makes the corresponding problem very hard. Optimization problem, when you're trying to build a model which certifiably goes towards satisfying a property. Right? And so what has happened is, despite best efforts and massive amount of work on this, really, if you look at like simple data sets like CIFAR10 and CIFAR10 and just some small perturbation regions, you are roughly around these parameters when it comes to building state-of-the-art models that have any form of certifiable guarantee. So you'd end up something like maybe 70% accuracy and some % of certified robustness. So certified robustness certainly goes up. Because if you don't do this kind of optimization, you'll basically get 0. But a certified robustness just means that we can prove that any point in this region here classifies to the same as the original image around which the shape is taken. But still, this is very far from from the accuracy that we get with normal training for CIFAR10, which is in the 98, 99% range. It's very high. And the question is, why is this not working? Okay, why is this constrained optimization problem not working? And and there were lots of works on trying different hyperparameter tuning, augmenting the data in certain ways, all kinds of things, running on lots of GPUs, but it really didn't push things too much, which is kind of surprising. And even a more weird thing happened, where not only didn't push things much in terms of numbers, but actually it turns out that more complicated symbolic transformers here worked worse than more simpler symbolic transformers work much worse than more complicated symbolic transformers. So if you do something like boxes only here, this actually tended to work better than a more complicated shapes that you could potentially get, which from a certification perspective makes no sense. The tighter you are, the more things you can prove. So why is this going on? And so this kind of begs some fundamental questions, like you see, like you're getting into these more fundamental questions. So one of them is there even a model? Does this model even exist, you know, with high accuracy that's actually certifiable to something very simple like infinity robustness, okay? So we kind of set to investigate these questions, and we were pushed to these questions because, you know, after hours and I don't know how many hours of running GPUs and other people running GPUs and TPUs and whatever clusters, things were not improving drastically. And I'm going to skip some of these things and basically tell you that the answer is, it's essentially universal approximation theorem of sorts, which says that, yes, it is true. You could approximate any continuous function essentially with a deep neural networks, for which you can prove properties with a very simple symbolic transformer. So what this thing essentially says is, yes, there is a hope for this optimization problem. Let's go back over here. There is a hope for this. The model exists, which you want, with the properties that you want, but you actually can't find it. This is unfortunate. So what do you do? So maybe you need better optimization algorithms. Maybe you need to pose better optimization problems. Maybe our optimization problem is not right. And so this was one paradox why we're not finding these models, even though they exist with certain guarantees. And the second one is the one I mentioned, the fact that more looser relaxations or looser abstractions, looser symbolic transformers over here actually produce better results. So absolutely no intuitive from a certification perspective. And so here's a basic hypothesis kind of that tries to explain this. It says that actually more tighter abstractions, more tighter symbolic shapes that you could get here, maybe something like this, something convex like this, I don't know. It actually leads to more difficult optimization problems. And so this is kind of intuitive, but you know, and so if you look at the numbers, this is the paradox of training machine learning models to satisfy properties. So here is your, you know, you're training with this method, which these are just different kind of symbolic propagators, and going down, as you see, the tightness increases, so they should be more desirable. They introduce less garbage points when you propagate shapes for the network. They're abstract, you know, symbolic activations, if you like, introduce less over approximation. So going down should be desirable for certification. So, you know, Crown or Deep Poly or Deep Z are great to work with. But when we're training with these things via that optimization problem, we are actually getting worse results. So this is completely strange. And what it turns out is that there's other factors other than tightness of relaxations and of the symbolic integration of symbolic propagation into continuous training that you need to consider. And these are these two properties of continuity and sensitivity. So what continuity means is that if your shift the weights of your network a little bit during training, which is what happens to the result of these shapes that we are showing? You know, how are they affected? And what it turns out is that this very simple method, which is essentially boxes, has very desirable optimization properties over here, while these more complex certification methods, symbolic certification methods, actually have not so great properties. And we're not going to get into these beans and names, you know, the number of combinations of reviews and fine layers combined, and the size of the layer and so on. But ultimately, as you go down, as you get more tighter, you actually get worse in terms of optimization. And so we kind of analyzed these symbolic propagators and found out these properties, and this can kind of explain why it may be hard to train machine learning models that satisfy anything. How do you actually go from here? So this is very unfortunate in a way, but it's also very fortunate because it gives us things to think about. And so there's much more still that needs to be done here. Perhaps there's other properties beyond continuity and sensitivity and tightness that we need to be aware of. And potentially one way forward is to think about other optimization problems, not like the one that I posted over here. So we need to think of different optimization problems, where is this going? For which you can actually enforce and train models that satisfy what you want. Okay, so there is this work that we actually did with Mislav, so the previous speaker. I'm not going to go into it in detail, but the high level idea is that it generates simpler optimization problems, and without so much compute power and label data, you can actually, again, by considering these ways to deal with the infinite data going forward, you can get much better results. So clearly, this is the way to go, it seems, but we are still very, very far from solving this problem. Okay. So this is what I wanted to tell you. If you want to know more, I guess some of you are already have taken this course, or maybe you haven't. In fact, the lectures are fully online, where we go in depth in some of these challenges. We actually put the lectures on YouTube because there was demand by other people outside ETH, and so everything is there in terms of optimization problems, difficulties, how to incorporate symbolic reasoning into the network, all these kind of things we talked about briefly today. If you want to know more, particularly about this kind of direction, you can go here to this website and find more about fairness, incorporating background priors, different kind of statistical or deterministic verification techniques, training systems, and so on. So that's what I wanted to tell you a little bit about the, if you want to do certification, you need to think about the infinite data. If you do think about the infinite data, you need to think about different optimization problems potentially. And we are not there yet in solving these, building models that actually do what they're supposed to do, probably. So thank you very much. I'm happy to take some questions.
Cool. So thanks so much, Martin. Are there any questions? There was a question on the chat, actually. Let me try to tackle that first. So the question is from Mariam, and she asks, how do you differentiate between accuracy and overfitting?
So a second, let me just take this here. So yeah, can you repeat the question? I didn't get this.
The question was, how do you differentiate between accuracy and overfitting?
How do you differentiate between accuracy and overfitting? Well, I guess, this is completely orthogonal to the talk here, right? It's this is the standard ways to test the accuracy, and the test underfitting, overfitting. This is completely orthogonal to like the symbolic techniques that we are showing here. So there are ways to do this, and you look at the training set. That's
Maybe I can shoot a question. So my question would be very high level, and I'm trying to connect it to the subsequent sort of a panel we have with regulators. And so I've seen in your talk that there's a lot of great work that's done in the sort of robustness community, trying to kind of put a lasso around these models and make them probably correct. But as you demonstrate, also it's a very challenging problem. So if I'm a regulator trying to leverage the knowledge that you have, what would be kind of the message you have for me? Like what are we able to do now in terms of state of the art, and what do we not know how to do, and what can I expect in 5 years? Things like that. Maybe that could be like food for thought and future discussion.
Yeah, I think it's a good question. I'm actually thinking about this ourselves. So I think as far as regulators, I think for a second, I think we should ignore what can be done, what cannot be done. So first, I think it will be very useful to when we talk about all these policies, fairness or bias or whatever policies we care about, we should actually have a way to express what those things mean in some, at least, mathematically formal way to specify what it is that we actually care about. So then I think that's already challenging, and that's something that we actually don't have. Even if you look at definitions, so like in individual fairness, what does it mean for two individuals to be close, right? That's something that we looked at with Mislav and with others. How do you define that two individuals are close, like in a parametric way, right? And so in a kind of simple declarative way. And so I think it's before we even talk about how to build models that do something, we should say what this something is. Like what it is that the model should satisfy. And so we need a language, I think, some way to express this mathematical, in a more mathematical way, what the properties are. So this is my advice. I would say, like, I'm actually quite interested to see these properties expressed. And then after that, there is many ways to go about it. Maybe you want, maybe we're fine with like experimental guarantees. Maybe, more like, experimental robustness. Maybe we are fine with, we want really hard mathematical guarantees which are deterministic. Maybe we want guarantee like the one I showed here. Maybe we want guarantees which are statistical, but still with some confidence. But I think the first question is, what are the properties and what kind of guarantees we want? And I think this is a bit missing, I think, in the whole space now. Like interesting specifications. That's what I think.
Yeah. So I guess in the regulators, they know how to speak law language. They don't necessarily know how to speak math. So then I guess there's definitely a sort of a bridge there a gap there that needs to be bridged somehow.
Yeah, I just had this discussion in this week with somebody. I think we really need people to sit down and look at some of these things and kind of regulations and policies and try to express in at least some semi-formal way what it actually means. And this, I think, could trigger huge amount of research, because for certain properties it could be more easier to build the systems. The optimization forms may be simpler or whatnot. But I think we're not there yet. I think we shouldn't worry about. I mean, that it's certainly hard to build models that do what they're supposed to do. But what is the specification? I think in general, the community at large lacks good specifications. And if you actually look at other research areas like NLP and natural language processing, some of the developments there, like the ACL checklist and others, are to do with giving specs that make sense for their domain, like synonyms, replacement, or insertions of whatever words. I think this is what we need. This is what's missing.
Okay, cool. Thanks a lot for the insight. And let's thank the speaker once more. And with that, we will close briefly to restructure our stage and get ready for the upcoming panel. So to the viewers online, please stay tuned.
See you guys here.
Hi, everybody. Welcome. And thank you for joining us today. So our panel is part of the Europe Day of the two-day workshop on data-centric AI. And as you know, this is jointly hosted by the Stanford Institute for Human-Centered Artificial Intelligence and the ETH AI Center. My name is Shalini Trefzer. I work at Microsoft Switzerland as a data and AI specialist, and I'm your moderator today for today's panel on AI and regulation. With me on stage are the experts. Alex Eilich is the co-founder and executive director of the ETH AI Center. He is a remarkable, energetic person. He's been twice awarded Entrepreneur of the Year in Switzerland. And he co-founded the ETH spin-off Dacuda, sold it in 2017 to the augmented reality pioneer Magic Leap, where he was then responsible for building up 2 Swiss R&D centers on computer vision and advanced photonics. Alex brings in the valuable perspective of combining research, industry, and entrepreneurship. Shweta Shinde is assistant professor at the computer science department in ETH Zurich. She leads the Secure and Trustworthy Systems group. Her research lies at the intersection of trusted computing, system security, program analysis, and formal verification. Fabian Streif is the new head of economic development at Amt für Wirtschaft und Arbeit, Canton of Zurich. He approaches new technologies as key drivers, always with the aim of increasing this region's competitiveness, a good thing for all of you. He brings in the perspective of the Canton of Zurich as the economic powerhouse of Switzerland. Fabian was previously at Basel area Business and Innovation, where he was the head of innovation in healthcare, driving an initiative that addressed the transformation from pharma to a more personalized health industry, including digital health. Previously, he was co-head of the economic development of the Canton of Basel-Stadt. Stephanie Volz is the managing director of the Center for Information Technology, Society and Law, ITSL, of the University of Zurich. She studied and did her doctorate at the University of Zurich and worked for several years as a lawyer in a law firm specializing in commercial law before returning to the university to devote herself to research again. She brings today her important perspective in modern legal research. So we have a wide variety of perspectives from the experts here today, and we will explore the new technological, legal, regulatory, and administrative pathways that we all need to foster to facilitate innovation that builds bridges between global communities, like, for example, here in Stanford, and serve modern society. Increasingly, we live in a society and world that is absolutely inundated by data. So if I cast my eye down, for example, it's right here, even on my body, right? In the form of this Fitbit. So a challenge for all of you and whoever's listening online as well, I'm gonna count to 10. And I want you to cast your eyes down upon your own bodies and upon your belongings right next to you. So everybody look down, look around, and let's start counting. And I want you to see if there is anything that's collecting, transmitting, or displaying data. Just raise your hand up, okay? Let's go. A 1, and a 2, and a 3, and a 4, 5, 6, 7. I don't even have to go to 10, huh? Okay, how many hands? Stay up if you have this. Okay, very good. Hold it there for a second. Now, let me make the statement. I know exactly where, how, for what purpose this data could or should or must be used, and by whom and under what conditions. Any hands still up? No. Okay, so here's the conundrum, right? Bingo. So we've got something that could be of great value for humankind. It's literally surrounding us, yeah, data. How can we unlock this potential beyond a purely legal or regulatory approach? And that is the purpose of today's panel. So we've got until 5:45, and I'm gonna turn to Alex with the first question, which is, and we've been on 3 panels in 3 months, so I know this is important to him. What is your top of mind, Alex, when you think about pathways to unlock innovation with this incredible resource that's here everywhere, and all of the different ways in which we could deal with this data? What do you think of when you think of this question?
Yeah, so thanks a lot, Shalini, for the interesting question. So I think there are a number of aspects that we have already seen today, you know, why it's very hard to build AI-biased systems from the data perspective onwards. So I think it's super important to do the research there. I'm also concerned, like, how can we bring things from research all the way into practice to consumers? And the biggest problem that AI has at the moment is that people are concerned. You read a lot in the press what AI is supposed to be doing, taking jobs, prescribing what medication you get, and so on. So there's a lot of fear and uncertainty that's there. And also, of course, looming, what does it mean on the regulatory level? Does it mean that, like, everything gets regulated up to the detail and so on. And the concern is basically how can we find a way of protecting individuals, but still leveraging innovations. And I think this is something which is very, very important. And we saw, for instance, earlier also a talk referencing to GDPR. But if you look at what is behind there, there's still today the big picture of the way that we deal with data is basically just that you share or you don't share. And then we try different measures to mitigate back from them. And I believe that there are more technical approaches to the problem where you don't have to share the data. And we touched a little bit on decentralized learning and so on. But basically, it's not reflected yet on the framework conditions. And I think that's great while we have experts from the legal side and from the economic development side here to address, because ultimately, we should not stop, with something saying like, look, AI could be high risk, but we should phrase the question around how can we enable innovation in areas, especially like health and so on, that are highly personalized, that pose a low risk and basically still have high personalization in there. So this is kind of the key question that drives it. And people have in their heads two approaches. One is they think like the more data you collect, the better, where we also learned a little bit today that you need to have the relevant data and so on. And the other part is that I believe we lose a lot of the competitiveness if we early on in the data pipeline just anonymize it. Then we lose a lot of the value of that. So this is something that would be great to tackle, and where we have different perspectives here as well, where I'm very excited to talk about.
Sure. So basically, technology could be one pathway to deal with data, not just regulation, right? And then that takes us to Shweta's work. So Shweta, tell us a little bit, like, when we were discussing technological pathways, you mentioned cryptographic, you mentioned hardware methodologies. So can you paint a big picture of the highlights of each so the audience can sort of take that back and go research it a bit as well?
Yeah, sure. So when we talk about data in general, people usually worry about data at rest. So for example, you've stored it on a disk, you've stored it on your hard drive, somewhere else. Then people worry about data while you're computing on it, right? So let's say you're trying to do some inference and you've loaded the image and now you've inferred the label and so on. So all of this data is stored somewhere in your computer's memory and someone is operating on it. And then finally, people also care about data in transit, right? So when you want to exchange data with each other and so on. So these are the sort of main areas where people try to focus on. And in terms of protection mechanisms, there are, I would say, two broad options. One of them is essentially using cryptographic techniques, right? So we have techniques which encrypt the data and so on, so that when it's in transit or when it's stored somewhere, it's always encrypted, integrity protected. So no one, even if someone gets their hands on it, you don't actually lose your data, right? It's essentially useless to anyone who gets it. So that's nice. The problem actually happens when you're trying to compute on the data, right? And that's where, again, people have come up with interesting techniques where you can compute on data without ever having to decrypt it and so on. So that's one extreme. It's called homomorphic encryption. There are weaker mechanisms of it called secure multi-party and so on, right? So these are nice techniques, and it actually fits well in the kind of use cases we think about when multiple people want to share their data and they don't want to, show each other their data, but they want to like collectively learn something. So these techniques fit right into these use cases. The big downside, though, for large-scale adoption is that they don't scale that well, right? So you can probably do it with 2 hospitals or 3 hospitals, but doing it at a worldwide scale may not actually be computationally feasible. And so that's where the second pragmatic approach comes into play. People call it trusted computing. Essentially, what it means is that you have to anchor your trust into the hardware, and the hardware will then allow you to create safe sandboxes, right? And the sandboxes guarantee that no hardware or software on this and in this environment will be able to look into your data. And that's when you sort of do operations on plain text and so on, right? This is amazing because, again, it unlocks a lot of computational power. You can do things as you do it on your own personal computer, but with the assurances that no one will be able to snoop on it or tamper with it and so on, right? So people are exploring both of these options simultaneously. So that's the technological perspective or the security perspective of things. Now, the second stage where you sort of start worrying is, okay, no one is able to access my data, but what about the results, right? The results might start leaking something. And so this is where privacy concerns start showing up, right? And this is where stuff like anonymity and so on needs to be put in place at the right time. And then there are also correctness issues, right? Yes, you have differential privacy, for instance, is the term that people use. But then you need mathematical guarantees that your data is really private and so on. So I would say this is the spectrum of technical technical defenses that you have in place. And the nice part is everyone is actively trying to use these technologies.
To ask the panel what your experiences have been like. For example, let's say it's a collaborative effort and you're using confidential computing, which as I understand is really having a third trusted party hold your data. Is that right? So this way the collaborating parties do not see what the data is, even though they can work with it.
Yeah, so yeah, that's a good follow-up, right? So essentially in either of these techniques that you use, eventually you have to trust someone, right? So in the hardware-based mechanisms that I mentioned, you have to trust the hardware manufacturer, and then you can place this hardware, let's say, in the cloud service providers, environment and so on. And this is actually a service that people provide. Any major cloud service provider that you know of today sells this or advertises this as a confidential computing platform, right? And so the fascinating part about this is that you still get to outsource your computation. You get to access blazingly fast CPU servers in someone else's environment, but you don't have to trust them. And so this holds true for a single party. For example, if I am a hospital or if I am a person who has a lot of data, I can outsource it to the cloud without having to trust the cloud service provider. The tiny trade-off is that I do have to trust the hardware, right? And this scales to multiple parties. And so this is what allows multiple untrusted parties to then put their data on the cloud in a confidential environment and operate on it. And using cryptographic techniques, you can then encrypt data for special use cases, right? So even the hospital itself will not know what queries the service is getting. The patients will not know which all hospitals are participating in this and so on. So I feel like this style of computation really solves all the common concerns people have when it comes to sharing data or computing on shared data and so on.
And how is this working out in industry, for example? Like, let's say that you want collaborative work to happen in a given industry vertical. In your experience, for example, Alex, do you think that this is working well? Are like two enterprises able to collaboratively work on data without disclosing it or being afraid of losing their trade secrets?
Yeah, so let me try a different kind of answer. I would actually like to hear Stephanie's opinion, because it sounds like the solutions are already there. Why are they not used by everyone? Yeah. Like what is maybe missing?
I think what is missing is a good regulation which fits these things. I think that if we do this, we have already a lot of problems. And one of the problems we have is that you said before, Alex, that people are afraid of technique. They don't understand it. And that's why they are afraid. And that's why we do a lot of like privacy laws, like the GDPR we have. And this, for me, it blocks sometimes innovation. And I think we have to more think about the good things which innovation can bring, and then adopt the law to these things.
So would you say that fear is one of the biggest challenges, or are there other really significant challenges in Switzerland? Let's take Switzerland. So if you're talking about regulation of artificial intelligence or technology in general, what would you say are some of the big factors driving this?
It's important. I don't think that we have to regulate technology, but there are some things we need to rethink. One is manipulation. We have to to see which is the border between normal influence and manipulation. And the other thing is discrimination. And for me, these are two areas which need more research.
Okay. Could you talk a little bit more about manipulation? How would you know if a technology is manipulating you, or if a particular use of data is manipulative?
Yes, this is we have to research about this, but till now I think it's kind of influence which is hidden.
Yeah.
It's to the advantage of the manipulating person. And it's also like, yes, maybe we should think about protect some groups of people like children or something like this. This might be an element of manipulation. There I see like where we should think about the regulation, taking this.
Yeah, indeed. And in fact, this ties back also to communities, right?
Yes.
Because one of the things we discussed when we were thinking about this question is the fact that certain societies or certain circumstances may be more protective of society and make the society less manipulable, if you will. And there are other circumstances which can make a society more open to manipulation. So would you say that a well-informed society, I mean, how do they deal with manipulation? I mean, first of all, assuming that Switzerland is a well-informed society, and is this correct? And how do you assess that that plays a role?
Actually, I thought we have two sides of manipulation. We have manipulation against consumers. And on the other hand, we have manipulation with regard to citizens as voters. And the second one is what we say like is an issue like from the perspective of disinformation. And before the Corona crisis, I thought in Switzerland, we don't have a problem with disinformation. But now I'm not sure about this.
Yeah.
And what I think is we don't need information, but we need education, like data literacy, we need media literacy, and yes, and so on. It's not a problem that we can solve maybe with regulatory, but with education.
I think that's a fascinating point because it ties then back to your work within the community of Zurich, for example. And this is happening, I'm sure, all over Switzerland. So please tell us a little bit more about this concept of data literacy among your citizens. How are you promoting this and what is the purpose of it? Are you educating people so you can push more innovative projects forward, or is it for its own sake? Let's hear about that.
Yes, thank you. I think I will start with what we are doing as an economic development agency. I mean, obviously we try to contribute to the prosperity of the society in the end, but the target group is obviously firms and firms creating jobs and sustaining jobs. But I think what we learned already here today again is like we shouldn't miss the society, and that's something we try to explore. How can we definitely address the society better? And that's why we started to say, let's start a dialogue with society, just go into small towns and have events and talk about human-centered AI. How can we really benefit from this technology? And what are also concerns that the society has? I think there we hope to really get to a level of education also that helps them to be aware of risk, but also to be more open to innovation. And I think if we get there, we have hopefully less challenges with regulation. And that would lead me then to the second point of that we can then really start foster innovation with data and approaches we have already heard today.
And what have you learned so far from your citizenry? Are they open to this sort of data literacy approach? And how can like the ETH, for example, and legal research tie in to the work that you are doing on behalf of a canton? Because you have more direct access maybe to citizenry and you can bring them together. How can all of you kind of feed into this approach? I think that would be interesting to explore a bit.
Yeah, it's a good question. But I think we are still exploring. I mean, obviously, we have all these communities in Zurich, and some of them are very well informed. And it's not about these communities that we are targeting. It's really about the people, the society, the broad society, which is maybe not really aware of it or not deeply interested and I think there we have to start with. And obviously, there ETH and University of Zurich helps us to then bring in the right knowledge and also examples of where technology bring benefits. And I think that's a mix of like academic inputs, but also very practical inputs. Like where do we see already use cases where we can see that it brings a benefit, but also what will be the future about it. And then this can tie back to a dialogue we can have with politicians and also with technology experts.
So you're trying to also educate the politicians, basically.
In the end, obviously, yeah.
Okay. and how is that effort going? Why don't we maybe also from a regulatory legal perspective? What is your experience? Are they open? Are they willing to learn? Where are the challenges?
Yes, this is a problem I see that there not all of the regulators do really understand technology. I don't know how many politicians really understand all what we say about technology. And here I see an information gap. And this is why the legislator is like, oh no, we don't do this. This is, this is.
So they are really looking at their constituency, so their people, basically. And we are also trying to educate them in the same breath about technology, about how to push innovations forward, the concepts that they need to know in order to go and really make good laws, right? So then data literacy plays a role, because if their constituents understand where things are heading and they vote for a certain policy, then I think the policymakers feel more comfortable that, okay, this is the direction my constituency wants me to go. So that could be another vehicle.
Yes, transparency leads to trust.
Yes.
And now then we can use it better. I think it's important that we all work together, like people from technologies, with lawyers, with regulators, and everybody work together to have, in the end, a good thing which fits for all and has the best.
That's super. And I want to actually ask this question to you, Alex. So Stephanie mentioned trust and building trust. And that is a huge part of literacy, is saying, okay, I trust in, whatever, science or this kind of technology or this type of methodology of protecting data. So let's explore this piece a little bit. Trust also means that the models that artificial intelligence is deploying are not discriminating against you, right? So this brings us back to that second piece of legal research, manipulation and discrimination. So discrimination, let's talk about that a bit. What are we doing to include more voices in the development of models, in ensuring that such a thing as discrimination is minimized? How do we look at this from your view as an educator and entrepreneur?
Yeah, so I mean, so you see, like one thing that is obvious in this discussion, it really requires an interdisciplinary group to work on it. It's not possible to do it just from the technology point of view or just from the legal point of view. And that's why I think it's really great, to work with Stefan, work with Fabian and so on. So taking one step back, I think like all of the risks like discrimination, filter bubbles, and so on, if you look at it, the companies that have created those issues, they base on business models from the early 2000s, which basically are, let's collect all of the data and then optimize somewhere in between. This is why I think it could be very interesting to explore that today you have just your option to join this social network and then you share everything, right? Or not, right? And in reality, it's not a choice because all of your friends are there. So 90% of the people are there. So you don't have a choice. And this is where I would like to see some more creative options. Like, for instance, maybe you need a third option that says, I don't share, but I allow secure data processing. We need to define what that is, but basically that it would not give the data to the single company that can do a lot of things there. This would be things to explore. And I think what's also interesting on this group, and then I think if we are at this model then the potential for misusing the data is also completely different. So because if a single party has that and they need to optimize revenue, then it's very hard, right? So this, I think, could help. And the other thing, which is also quite nice, also similarities, maybe like because we have this event jointly with Stanford, I think in Switzerland, it's a very federalistic approach. So each canton can actually push things forward. And this has been known already successfully for the fintech, for the crypto area, where there was a close dialogue between the regulators. So we're trying to replicate this. And I think the US has also, with the states, a very similar approach sometimes. And I think that's why I think there might be a couple of similarities to explore as well.
No, that makes sense. I mean, California is really at the forefront of so many policies that are kind of groundbreaking. So it's quite interesting. And back to Shweta. So let's say that of the topic that Alex had touched upon, right? Like, let's talk a little bit about how would we technologically work on this discrimination concept.
Okay, so depending on who you ask, people will either say it's not a technology problem, or they will say it's a data problem, it's a labeling problem. Okay, and a very sort of, to be very extreme, people also say technology is not discriminatory, right? I'm not building technology to be discriminative.
But what if we did the sharing?
Right, exactly. But the people who use the technology, there is incentives. People have privileges and so on. So when you put technology into society, suddenly it becomes discriminatory. Right? And so,
gee.
Right? So if you had asked the same question to a different audience about, does everyone has a smartwatch? Maybe the answer would be different, right? If you go to India and ask this, probably no one will have smartwatches in an audience like this. And so, the places where data comes from is sort of leads to biases. From an algorithmic perspective, one nice part is that academics are painfully aware of this, and although we are not as active as lawmakers and so on, we take it as a responsibility that whenever we come across such discriminatory algorithms, we sort of shed light on it. There has been a lot of debate in the last year about discriminatory data models, usage of these models in situations like deciding imprisonment terms and so on. So as an academic, I think one thing we have been doing is building mathematical ways of quantifying discrimination. Or is there a way to actually find out evidence that something has gone wrong in the algorithm? And so, as we say, detection is the first step of fixing research. Right? And so we have been doing all of that, but it's not purely a technical problem from my perspective. You need transparency from where is the data being collected, where is it going to be used, what are the hidden incentives of people who are trying to use it, and so on.
And if you were to say, okay, I choose what I share, but it's not yours. I don't give you my photos. I give you permission to use my photos. From a technological perspective, is this possible? How possible? How practical is this to actually implement on a large scale for a society, for example?
Okay, so I would say this is absolutely possible. In fact, that's what we do for programs these days, right? Instead of saying, do I share my photograph or not? We say things like, can I share the location or not? Can I use this location to infer something about it? So all of that mechanisms are already in place. One problem is are they being implemented correctly? This is what we saw with GDPR, is that there's a law, there's a clear way how to enforce it, but people find shortcuts of bypassing that. So faithfully implementing the things that you expect is one problem. But I think that's a technical problem. There are, again, ways to enforce it. So yeah, from a technical perspective, it's absolutely possible. And in fact, surprisingly, it also scales well. There has been a lot of research in this area about scaling these kind of limited computations and so on. Especially with specialized hardware, it's absolutely possible. The problem is knowing what to share and what to not share. For instance, if you have an Apple iPhone today, users are being asked, should you be sharing this? Should you be sharing that? And everyone gets irritated, right? Like, I want to click a picture and a selfie. Why are you asking me 10 questions? Right? So the technology cannot help you there. You have to input, you have to feed that input at some place. And so I think my stance is the technology is there. It's a usability problem at this point.
I mean, it's this information overload, isn't it? I mean, it's all over the place. And like, let's take your community, for example. If you're a lay citizen and you're being asked 10 times a day, do you want me to share this or that or whatever? It's irritating, isn't it? And yet you as an individual want to control your own data as well. So how do you approach this? Like you want Zurich to be an economic powerhouse, which means that you want your citizenry to be digitally literate. What are you hearing and what are you saying in terms of how this line should be drawn between what is shareable, what is not shareable? How do you protect your people?
I think that's a very hard question that I always pass to Alex or Stefan.
They had their turn, now it's yours.
No, obviously, I mean, that's not something that we as economic development agency kind of can influence. I mean, that's a thin line and it's always a balance that we have to find, right? And I think the dialogue helps to kind of guide a bit and feel what we can do. I mean, I would more like to come back to educating also politicians, because for that, one is literacy and the other one is like demonstrate that innovation can really help. And there I see, I mean, use cases that can help the public administration, because the Canton of Zurich has many challenges, but also use cases that helps the society really for the greater good. And I think there we can maybe also shift the needle a bit to, okay, yes, I have to click and I have to deal with all these things as a private person, but it's okay because I can contribute to something bigger, right? Mm-hmm. And that's I think something we try to explore if they can help. And there the idea of what we also have already discussed once is like idea of a sandbox where you can really approach or get access to data we have around. I mean, there's plenty of data around in the kind of Zurich, great data for also different approaches and use cases like pollen load or things that really the greater public has to deal with sometimes, right? And there I see many great cases and startups that have technology in place, and it's more about get me data and help me to really deal with regulation. And I think there it would be great to really help with a kind of a sandbox approach.
Indeed. And that is what I wanted to ask you next is you're having this dialogue and you've got a vision. You want Zurich to be this absolutely amazing example for Switzerland. And you've got this thought around innovation and startups and sandboxes for them. So let's talk a little bit about what success looks like for you. And then I have a quick question for the audience.
Yeah, obviously, I mean, success would mean that as economic development agency, that Zurich is really well known as kind of an AI place where you as talent or as company would like to go. I mean, that's my very personal kind of what means success. But for a sandbox, I think it would be really great that we can demonstrate use cases that have used the sandbox and have realized, okay, we can make a difference, and that we can show that to the politicians. And that would then mean that maybe we can shift the needle a bit and start changing regulation. And that's, I think, the ultimate goal we have. So it's really a way to kind of influence a bit how we deal with regulation.
Wow, that's great. It's an ambitious goal, but
I agree.
Yeah. So to the audience members, ask them something that is of relevance to you, because you are all involved with the ETH somehow, right? Is there anyone among you who will be looking for, let's say, a job or funding in the next 3 years? Anyone here? Okay. 3 years, 4 years, 2 years, 1 year? So you ask the question. So what we've learned so far is that, look, I mean, there's so many, essentially most of us are going to do some kind of work dealing with data. And we know that there's possibilities around using technology. There's possibilities around using this kind of like an interplay between different functions. There's a possibility of looking at regulation from a different way, educating politicians, data literacy, etc. All this is going on. So if you had access to this panel of experts, how would you want them to help you to succeed?
We started to talk about these kind of things. It actually somehow seems obvious to me what the solution could be. So actually in the beginning, so I thought, oh, what these guys are talking about it. So it should be very simple and obvious. But now when we actually somehow go down and then actually somehow talk about it more, and I thought that maybe it's a really complicated task because it's really related to the people, to the community. And when it comes to the people, it is very, gets very, very difficult, in my point of view. So, but maybe my question would be, first of all, what is your horizon in general? So when we talk about, for instance, the Zurich canton, and we're going to have a digital city or more AI-centric city in the end. So what is your horizon? So we are talking about 10 years, 20 years, 50 years, 5 years. And so because it's really different, we're going to educate the people who are now in bachelor's studies or the people who are in the middle primary school, what would we would like, or I don't know, maybe adults or old people, which people we need to somehow increase the education, their understanding about the data, the AI, what it could be helpful, where it could be dangerous. So what is actually your general horizon maybe in this context? Yeah.
Want to start?
Yes, I can start. I mean, we don't have a 5-year plan or something like that. No. I mean, obviously, we definitely think that in the next years, talents is a big challenge for the industry. And we know companies that have 15,000 jobs they would like to be created in Switzerland, but they really struggle to find talents like you. So that's the great news, right? But obviously, I think it's not about you and educating you, but it's about educating the whole society, because otherwise we have these different levels or different layers of communities which are not communicating to each other. And I think that's a challenge, because then your solutions cannot really be applied. And I think that's something we would like to avoid, because your companies should stay in Switzerland, obviously, and for that you need the right framework conditions.
So we're coming to an end of the panel quite soon, but let me just phrase it back. I think this is an emerging field with tons of new business models and jobs being created. Potentially companies that were started 20 years ago disappear. So I think this is the place. So I mean, how can we make it easy? The people like you are shaping the future is kind of the main concern. I think it starts now, and this is why we're here and having also the dialogue. And I want to give back to you to close it.
Thank you very much. And I'm sure others have questions too. We're closing the panel, but what I hope you will do is contact these specialists and experts and make connections, right? Because ultimately, as Alex said, the more we talk and the more we sort of help each other and do this interdisciplinary exchange, the better we can support our society and move us forward into this new era. Thank you so much for listening, and have a great evening. Thanks.
Okay, great. Thank you guys so much. So now it is the time that we transition this and hand it over to our colleagues at Stanford. So we will end this stream, and for our local audience, there's food and there's water, right? Take a break, and let's come back at 6 p.m. Then we will call in to the Stanford session, right? And we are going to talk more about the benchmark effort. Yeah, for those people watching online, right? So go to the HI website, you will find a new video there, and hopefully to see you guys there. Yeah, thank you.